Okay, so let's rattle through a few things, and then I'm going to dive into what I'm actually supposed to be here to do. First of all, how many of you use the IPython notebook? Okay, go to nbdiff.org, make this work, and then get Fernando and Brian to integrate it into Jupyter. This is a tool built by some undergraduates in Montreal as a one-term project that allows you to diff and merge IPython notebooks. It integrates with Mercurial and Git. Okay? Because here's my problem. I organize and run workshops where we teach scientists how to program. What do we say on day one? Everything you care about should be in version control, and as a result of that, you should not use things like Microsoft Word and Excel spreadsheets because you can't version control them. Try doing diff or merge on a .xls file. Right? Does not work. What do we do on Tuesday? Here's the IPython notebook. Isn't this really cool? Stick it under version control and try to diff it, where they've got 68 megabytes of base64 encoded PNG and some very carefully indented JSON. You must be this tall to go on this ride. Okay? I feel foolish when people notice that Monday and Tuesday I'm telling them very different stories. If undergrads can throw this together in one term in Montreal, in winter, right, when two of them don't drink caffeinated beverages at all for religious reasons, we can do this. And something I'm going to come back to towards the end of the afternoon. We want to teach, and I'm going to be talking for most of today about good teaching practices and how you can improve your teaching practices, but we need teachable tools. How many of you would like to be rich, famous, and popular while making the world a better place by writing code? Okay, here's what you can do that will bring more human beings to the nirvana of version control than anything else I can think of. And it requires 3 competent software developers for 8 months. That's an estimate from somebody on the LibreOffice team. I want you to make diff and merge work for Excel spreadsheets. It is embarrassing that we cannot usably put one of the world's most common and useful document formats into version control. An Excel spreadsheet is a chunk of XML. We know how to diff trees. There is absolutely no reason other than self-centered, lazy arrogance that software developers have not made this possible a decade ago. And if we can stick spreadsheets into version control, we remove one of the biggest obstacles we face when we're teaching, which is, here's this really cool thing over here. You have to throw away everything you've been using for the last 10 years in order to adopt it. You have to give up on your Word documents. You have to give up on your Excel spreadsheets. You have to say, I've been wrong for 10 years. Nobody's going to come over. As a bonus, if we make Excel spreadsheets play nicely with version control, then the people in university accounting departments that we have to work with in order to get our budgets approved might finally start to use tools that we like. There was a very sad period in my life when I was a version control system. I was working at what is now the Edinburgh Parallel Computing Center, and the deal for this 6-site collaboration was, by midnight Thursday, you have mailed all of your code changes to Greg. By 9 a.m. Monday morning, he will circulate a merge of those changes, because I could not persuade physicists at 6 UK universities to adopt CVS, but they would use email. This was not the happiest 6 months of my life. Okay? If we can make version control work with spreadsheets, we can bring millions of people, literally millions of people, most of whom do not think of themselves as programmers but have control over our lives because they run our goddamn budgets, to come and use our tools. 3 developers, 8 months, starting with LibreOffice, which can parse the files, which can present them. Tree diff is well understood. We can do this. And we should have done it 10 years ago. And all of your colleagues who are still using Excel will finally have a ramp rather than a cliff to climb. I am making a plea. I will get down on my knees and beg if I think it will do any good, okay? I have no shame when it comes to this, because if you can do this, I can get a lot more people to start doing things our way, and our lives get better too. Please.
My point was just, and it's more for the IPython notebook than for Excel, but it's for both the case. Maybe it's just that we have the wrong persistence model.
But we're stuck with it. How many of you learn? How many of you use English as a second language? Did you enjoy learning the rules of grammar for English? How about the spelling? Right. Okay, but we're stuck with it. I go to the United States, I have to measure distance in miles and feet. And I have to remember that 6/7/2015 is not July 6th. Because it's embarrassing to show up a month late for a talk you're supposed to be giving. Okay? Okay? Like, who the hell measures distance in feet, inches, miles, right? Month, day, year. So, anyway. A couple of other things, then I'm going to dive in. I just want to clear all this stuff out of the way while you're all getting settled in. How many of you care about reproducible research? Yes, stop. Okay? Doesn't matter. We can't, and by doesn't matter, I mean we can't sell that idea, and here's why. Assume 5 million scientific papers were published in the decade 1990 to 2000. That's an underestimate, right? But let's assume it was 5 million because it's a nice round number. In the 15 years since, at best or at worst, maybe 100 have been pulled because somebody botched the computing. Not talking about outright fraud, I'm talking about somebody screwing up the computing. So work the numbers backwards. How much extra time should you put into computational reproducibility as insurance against 100 over 5 million? Turns out it's worth 115 extra seconds per paper to worry about reproducibility. How many of you have had a paper pulled because you botched the computing? Published paper yanked. Okay? 1 degree of separation. How many of you have had a colleague pull a paper because the computing was botched and it got detected after publication? 1 in the room. And this is in a very computationally literate audience. For the better part of a decade, I tried to convince scientists to come to software carpentry workshops and learn better computing skills by scaring them. Do this or you might be wrong, and here are the 3 scare stories I actually have. All right, Jeffrey Chang and 2 others. It didn't work. They didn't show up, they didn't care, because they can do math. Surprisingly, most scientists can do math. This is a bad place for another joke about economists, so I'll skip that. After 2007, we began talking instead, not about the stick, but about the carrot. We began emphasizing the increase in productivity. And every scientist cares about that. Every scientist wants to get more research done. We believe that the sort of training software carpentry offers buys you half a day to a day a week for the rest of your career, or until you get tenure, at which point you're put on committees and you never actually get to do any research any longer, but you don't know that yet. Okay? At that point, we see an uptick in attendance like that. We can't keep up with demand. And this ties back to some well-known results in psychology. If you scare people, they become more conservative. And people in the climate change community have slowly started to realize this. If you sell fear, people will hunker down and keep doing what they've been doing because they know at least they're going to get fed. If you want people to change, you have to offer them hope. You have to offer them a better future, not a scare story. So if you want your colleagues to adopt better computing practices, don't frighten them with boogeymen. 100 over 5 million isn't that scary, and it's certainly not compelling. Talk to them about how much more research they will get to do and how much less time they will spend banging their head against software. Right? You have to understand the motivations of your audience in order to get them to learn. Okay? At which point, I want to switch over to this. If you take away one thing from this afternoon, get and read this book. In 2010, a group working in the Learning Sciences Institute at Carnegie Mellon University, who were tired of telling professors over and over again, we actually know stuff about how people learn and about how to teach them, those are not the same thing, sat down and wrote one of the best pieces of secondary literature it has ever been my privilege to read. 300 pages summarizes everything we know from experiment and study, peer-reviewed study, about how human beings learn, about what drives them to learn, about how to teach them. It is not an exciting story, but it is an engrossing one. It's not full of cute anecdotes. That's my job. I tell lots of stories, some of which are true. But this is science boiled down to something that a non-specialist can go through, and every couple of pages there is a useful, actionable result. For example, what are the 2 strongest demotivators of learning? If you want to suck the energy out of somebody and make them not care about your class, what are the 2 things that rank above all else? Anybody? Think about your personal experience. Have you ever been in a class where you just thought, I don't want to be here any longer? right? I'm going to get through the exam and then I'm just going to garbage collect everything I learned, okay? Why did you feel that way? What made you feel that way?
Because someone told me that I would not be good enough.
Okay? Others?
Yes. Would you really need this?
The two biggest demotivators, and this is a cross-cultural result, indifference and unfairness. If the instructor doesn't care about you or the material, you won't care either. And you've all had classes where the professor showed up and it was clear that they didn't want to be there, right? You'll never be more excited than the faculty member. Number two, unfairness. If you believe that people are being treated differently for no good reason, even if you are the one getting the preferential treatment, it will suck the energy out of you. Because, of course, there's always the chance that the sign will flip and you will now be on the unfair side. Okay? All species of higher primates seem to have a notion of fairness. Chimps, gorillas, and orangutans will all go hungry rather than allow people, or rather fellow primates, to have unfair shares, even if they're the one getting more. Right? It's wired into us at a very deep level. So whenever you are teaching, computing, or anything else, those are the two things that you have to avoid at all costs. If people believe the system is unfair, you just lost them. If they believe you don't care, you just lost them. If you avoid those two mistakes, at least you're on the playing field. Chapter 4, right? And in there, if you disbelieve what I've said, you can do what scientists are supposed to do, which is go and look at the references to the primary literature and decide if you believe the studies and if they are still up to date. This book is now 5 years old, right? We get new information. So this is science and it's bloody brilliant. How many of you have kids? Okay. I was starting to read this at the same time as my daughter entered primary school. It's really useful to be able to fact check a school board in Toronto being run by a clique of people who think that vaccinations are the same thing as genetically modified organisms and are both evil. Because if they believe that, what have they got wrong about teaching? The answer is almost everything. Right? For example, how many of you have heard about learning styles? Some people are visual learners, some people are audio learners. There is absolutely no evidence that this is true. And even the person who first proposed the theory has since retracted it. There is absolutely no evidence that different people have different preferred learning styles or that addressing those learning styles improves learning outcomes. But there are dozens of companies now pushing really hard to sell teaching materials built on that myth because they can make money that way. The truth is not going to help their bottom line. Okay? Chapter 5, along with citations to the literature so you can go and dig into it yourself. Much of what I'm going to give you in the next 2.5 hours is drawn from this and from other literature that this pointed me at. I want you to be skeptical. I want you to be scientists. If what I'm saying doesn't make sense to you, grab this and tell me if I've got it wrong. Tell me if I missed or misunderstood something. Because one of the other things I need you to know is that I am not yet a specialist in this area. I have been reading this literature for about 5 years. 5 years after you started your undergraduate degree, you were not an expert in what you currently do. Okay? I'm one chapter ahead of you. So take everything I say with a grain of salt. I'll do my best, but I'm sure I will get some things wrong. Everybody okay with this so far? Any questions at this point? Are we having a good time? Can I get a hallelujah? All right, ladies and gentlemen. Now, if you want some lighter reading that mixes in some interesting politics, I really like Elizabeth Green's book, Building a Better Teacher. She recapitulates 50 years of failed attempts to reform the American public education system. And everything she says applies to the United Kingdom, to Australia, and to Canada. My apologies, I don't know enough about continental Europe, Latin America, to tell whether or not these lessons have applied there. Here's the fundamental problem. There is one practice which has been demonstrated to improve educational outcomes at scale, and only one. And that is what the Japanese call Jugyo Kenkyu, lesson study. How many people here are musicians? Okay. What do you play? Bass. Bass guitar, what kind of music?
I used to play punk, now I'm older.
Yes, and? My daughter is 8 and she thinks the Clash are still touring. I'm not going to break her perceptions. Okay. One of the things that you do as a musician is you go and listen to other musicians, right? You've probably listened to thousands of hours of music, maybe tens of thousands, and that feeds into your playing. And you don't just have it on, you actually sit and listen. What are they doing, right? That sort of reflective study of what other people are doing turns out to be absolutely essential for the development of expertise. As far as we know, expertise does not emerge without reflective practice. I used to play jazz saxophone, and my teacher said, at some point, if you want to be good at this, you have to lock yourself in your bedroom for a year and listen to the following albums over and over again until you can do what they're doing, right? How many of you have ever voluntarily gone in and watched somebody else teach in order to see what their teaching technique is? How many of you have done it for thousands of hours? How many of you have had other people come in and watch your teaching in order to see how does he or she teach this lesson? How am I going to convey the fundamental theorem of calculus or basic Newtonian mechanics? Here's a stat. In the American public education system, the average teacher, K to 12, that's kindergarten through grade 12, has another teacher in her classroom 5 to 6 hours per year. And that other teacher is almost always there to evaluate the teacher for the purpose of promotion. Right? The principal comes in and watches you teach and ticks off a few boxes and says, yes, you get your raise. In Finland, the average public school teacher has another teacher in his or her classroom 3 to 4 hours a week and expects to spend an equal number of hours in other people's classrooms in exactly the same way that you would go and watch other punk bands and say, okay, what are they doing? What can I take away from this? We learn from each other. This is not commonplace in English language school systems for a whole bunch of historical and political reasons. There are a few places where it has become commonplace. All 5 of the countries that come at the top of the PISA rankings, the international comparison of K through 12 learning in math and science, do this routinely. And when schools adopt this practice, outcomes improve, even when you normalize for things like economic background. You can do this with poor kids and it works, because you always have to control for that, right? The problem is you can't get the people who run the educational system to allow the hours in the week for teachers to do this. And if teachers have to do this after hours, it's cutting into their family time, their prep for tomorrow, the forms they have to fill in for the school board, and so forth. So for 50 years, English language school systems have been looking at one of the artifacts you use, standardized testing, to help teachers figure out what they need to improve, and then done nothing with that. They have not then provided the teachers a way to improve their teaching. They just say, you're doing badly. And that's the end of the story. You're doing well. And that's the end of the story. There is no attempt to transfer your teaching practice to him or vice versa. Okay? When we run software carpentry workshops, instructors teach in pairs. One person is up at the front teaching, and I'm going to pick on Nell. Nell is going to be at the back. Part of her job is to watch over everybody's shoulders and see who's tuning out, who's having trouble, who needs an intervention. But part of it is she's watching me and seeing what I do. And when we switch up, she'll be teaching and I will get a chance to see what she does. And that's how teaching practice propagates. You get to learn from your fellow musicians. This is a really readable story about how that discovery was made in the United States and ignored, but adopted in other countries. Okay. Finally, I love this book. Therese Houston shows up at Washington State University, new hire in biology. What she does is microbiology. And the chair says, great, welcome aboard. Here's your office. Here's how you get your parking pass. And you're going to be teaching the ecology course starting next week. And she says, excuse me? I haven't done ecology since I was an undergrad. And he says, yes, but that's the course we need somebody to instruct. And you're starting next week. How many of you have ever had to teach stuff without what you felt was adequate time for preparation? Okay. Nell was watching me write this at 1:30, right? This is a collection of techniques you can use and funny stories, and you will recognize all of them, right? How do you fake it? How do you stay one chapter and then by the end of term 1 page ahead of your audience? There's a lot of really good practical advice, and this is a beautiful example of what Elizabeth Green is talking about when she talks about Jugo Kenkyu. This is somebody saying, here are my practical teaching practices. Right? This is what I do. It's not quite design patterns, but it's pretty close. Here's something, here's the context. run with it. Okay? Everybody okay with that? So these are some of the things I'm going to be drawing on. So let's take a look at what we're doing wrong. This is Mark Guzdial. His group at Georgia Tech has done fundamental, beautiful research on how we should teach programming if the things we care about are, number one, how much the students retain, and number two, how many of the students we retain. The first is how much do you remember? The second is, do you carry on and do more computing? Those are their two metrics. Not did you get a job at the end, but did you remember stuff and did you stay with the program? Absolutely beautiful research. So here are 10 myths. Number one, lack of women in computer science is just like all the other STEM fields. Well, this is looking at the US advanced placement exams. That's computer science, and this is a log scale for gender imbalance. The size of the circle shows you how many people took the exam. So way up here at the top, we've got studio art drawing. Okay, predominantly female, small number of people. You can see the clusters, and we've got physics, calculus. And here, anywhere in about here, we're looking at statistical noise. Down here, computer science. It's a huge outlier, even within the sciences, right? Now, there are still a lot of people who believe this is related to, for example, innate cognitive differences. Okay? That has been conclusively disproven over and over again. See chapter 2 of How Learning Works. Okay? We understand many of the reasons that produce this, we just don't have the political will to fix them. Myth number 9. Getting more women in CS, we need more female CS faculty. Turns out not to be a correlate or a predictor. Right? We don't have to do it that way. Good CS teacher is a good lecturer. No. We're going to be talking in about an hour's time about active learning strategies. We now have 25 years of research to show that me standing up here talking at you is a really lousy way to convey information. Okay? There are better ways to teach and learn. And by better, I mean for the same investment of effort, they produce better outcomes. And the first is as important as the second. There are many techniques that produce better outcomes, but are horrifically time expensive. One-to-one mentoring, for example, with everybody in this room, is going to produce much better outcomes, but would require 50 of me. That's not economically feasible. So what can we do with the same investment of effort? I'm going to show you something in a few minutes. Okay? Clickers and like are an add-on for a good teacher. No, absolutely not. Right? Turns out the tooling is really important. Student evaluations are the best way to evaluate teaching. There is absolutely no correlation between the rating a student gives for a course and how much they actually learn from the course. Right? Some of you may have seen that result published. Okay? So why do universities continue to hand out those evaluation forms at the end of courses? Does anybody know? Promotion? So it looks like they're doing something. In 1964, General Motors found that if they asked people, what did you think of the service in the shop, and then threw away the responses, people were still more likely to come back because you've given them the illusion that you care. Okay? If you can, it is very, very rare for research-oriented universities in the United States, Canada, the United Kingdom, and Australia, the 4 systems I'm most familiar with, to give a damn of any size or magnitude about your teaching evaluations. You're evaluated on your research. But we have to let the peasants know that we're listening. Right? We have to allow them their little summer festivals. Right? Good teachers personalize education for students' learning styles. No. Flat out wrong. Okay? It's a myth. It's being perpetuated by a handful of companies that are trying to sell teaching materials. High schools just can't teach CS well, so they shouldn't do it at all. No. The problem is there are so few people who have actually been trained in how to teach CS. So again, in English language systems, and the UK is now trying to change this, almost everybody who teaches programming has a background in business studies, maybe math. They have no more computing than most of the kids they're teaching. That doesn't make sense. Another one that's US specific. All you need to be a good CS teacher is to model good development practices. Absolutely not. The majority of people that we want to teach computing to are not going to go on to become professional software engineers. So if we orient our teaching right from the start towards producing them, we are alienating the majority. That's not going to help. Equally, what you do while you are learning is often very different from what you do as an experienced practitioner. The technical term for this is scaffolding. Right? You do different things when you are playing guitar as a novice than you would do if you are Jimi Hendrix, because if as a novice you try to do what Jimi Hendrix does, you're going to lose a finger. Right? So you don't do it that way. I can't speak, I honestly don't know much about guitar, but I know that what you teach a 5 or 6-year-old about breathing when they're playing the saxophone is different from what you do if you are an experienced player. Right? Because the kid can't do those things yet. They physically don't have the musculature, for example. Okay? So the idea that we have to teach C++ in the first-year course in engineering, which many schools do because that's what people use, is fundamentally wrong-headed. The idea that we should dismiss block languages like Scratch because it's not what real programmers use is fundamentally wrong-headed and damaging. Okay? And finally, some people are just born to program. Absolutely not. No evidence for the geek gene. Right? What we have here is selection and filter bias. Okay? We look at those who prayed and were saved and ignore those who prayed and were drowned. Okay? So, I've been talking at you for a while. If you want to see a few recent results, I will pass around this link. There was a paper that came out last year. Here are 4 evidence-based results. Number 1, if you're teaching classes, have the students pair program. It will improve retention in both meanings of the term. Right? It will give them somebody who can fill in some of their gaps, and if they are the more knowledgeable member of the pair, they will learn from explaining to their partner, and if they're both lost, at least they'll be lost together and feel less isolated. Using pair programming in introductory programming classes of all kinds improves outcomes, and turns out to be a practice that many of us use in the real world. Double win. Citations are in there. Okay? So do that. Media computation. This comes back to Gusdale and Erickson. How many of you introduce programming by having people, for example, write a loop that prints out the squares of a bunch of numbers? Okay, don't do this. It's not an authentic task. What Gusdale and Erickson did was run in parallel 3 different introductory programming classes at Georgia Tech for the better part of a decade. One of the 3 approaches clearly outperformed the other 2. In their introductory programming class, which used Python, the very first program that you write, the very first things you type into the Python interpreter are open image, resize, save, view. 4 things that are likely to work right, that do something that you believe you want to do in the real world because you understand why we would want to resize photos. And if it goes wrong, you get immediate feedback. If you only resized on X and forgot to resize on Y, rink. So rather than having this text spewing up on the screen and the numbers aren't sorted correctly and you don't know why, you've got a handle you can hold on to. I must have forgotten to do height. How do I do height? You know where to start the debugging. You're not just lost. Makes almost a full standard deviations difference in outcomes to the 2 senses of retention. Makes almost 2 standard deviations difference for women and minorities. The groups that are most likely to drop out as you give more authentic tasks are more likely to stick with it. That's a powerful result. And this is the reason why, 3 years ago, I rewrote the introductory Python lesson in software carpentry so that the first thing you do is open a CSV dataset and plot it. Your first 4 lines are read that data and plot it. Scientists all have to plot data. Right? That's an authentic task. Once you've done it, I can say, now let's plot the min and the max. At which point, the data is clearly smoother than it should be. Huh. What about these other 19 data files we have? Okay, let me show you what a loop is. A loop is a way you can take those 4 lines you just wrote and do it for each of your data sets, because scientists have to process multiple data files. First year chemistry class, you're having to do this. So in the computing you're learning at the same time, I'm solving a problem that you've got in your chemistry class, and by 20 minutes into the lesson, you've seen that this data is almost certainly faked. And you've got a skill you can transfer to something else you have to do. I got this idea partly from Gusdale and Erickson, but also from a group at the University of East Texas, which teaches programming to biologists, and they use a plotting first approach. Their entire first term course is, how do I plot this? Except they're not trying to teach you the detailed syntax of, in their case ggplot2, what they're trying to teach you is, how do I do it for each file? How do I merge files? Oh, wait a second. How do I tell if the files are of different sizes or shapes so they should be merged together? So they can introduce all of the core ideas by solving problems that scientists actually have, one after another. The outcomes are like that. Okay? References to the literature.
Great.
Please.
Sorry. Did it make you drop the questions?
Absolutely. Questions are good.
I've got two little things. Yeah, so I'm intrigued about that because that sounds a really good way of introducing this stuff. But do you then find that these sort of, when they're not trying to do those sorts of things after, those particular things afterwards, do they have the understanding of the core programming concepts?
The question was, if they then try to do different things, do they have understanding of the core concepts? The technical term for that is transference. Okay? Can they transfer from this context in which they learned it to other contexts in which they should be able to apply it? For example, a conversation I heard earlier today here in Cambridge made it clear that somebody who had studied English history in, I believe, college somewhere in the eastern United States could not connect what he had learned with any of the buildings he was seeing around him in Cambridge. He didn't understand that that and the stuff in his books were the same. Okay? And it's a very common problem. You learn something in one context, and you don't know how to transfer it to other contexts. The answer here is yes. The skill does transfer. Right? Peer instruction. How many of you have seen peer instruction in action? How many of you know what peer instruction is? Okay. Let me show you something beautiful. Assuming the video plays. Okay. The teacher has put a multiple choice question up on the board. Okay? The students are looking at it and independently picking one of the 4 possible answers. Okay? They're thinking, they're thinking. They vote publicly. They commit to a position. Okay? In this case, they're using colored cards. You can use numbers. You can do it with holding up fingers. You can use clickers, right? But you need something that's public so that your neighbors know what you believe. Okay? 50% voted for the right answer in this case. Now, turn to your neighbors and convince them that you're right and they're wrong. Talk to each other. Okay. This is where the learning happens. Because the studies that have been done on this, and there are now 200-odd studies of this, show that during this period, I actually have to think about why I believe it and why you believe what you do. And this is where knowledge is going to transfer from those who know to those who don't. And when you have 2 people who are both wrong, they might simultaneously realize it because they see the inconsistencies in their position. Okay? We're talking. Okay? Vote again. Okay. Right? Inspiring music, fade out. Okay. Let me explain what's going on here psychologically. If you all understand something like loops in Python, you probably have similar mental models of what's going on. If you misunderstand it, the odds are very good that you all misunderstand it differently. You all have different misconceptions because you're borrowing bits and pieces of different worldviews to cobble together some voodoo story about what a for loop is. In order for learning to take place, I have to clear up those misconceptions, but I can't do that. There are approximately 50 people in this room. Okay. If there are, even in pairs, 25 misconceptions I need to clear up, I can't intervene 25 times. That would take the entire lecture hour for one step. Right? So I can't give you what you need most, which is correction to your misperception. Video recorded lectures can't do this either. Lots of studies going back to the 1960s, when it was TV rather than MOOCs, but they're really the same thing, showed that if you watch the same explanation over and over again, it's not going to help. If you didn't get it the first time, you're not going to get it the 15th. I am sure many of you have had the experience of asking somebody a question and they explain and you don't understand, so they say exactly the same thing slower and louder, like that's going to help. Okay, that's MOOCs, okay? And that's why they have such crappy results. What you need is individualized intervention. What you just saw was a way to scale individualized intervention. If I get you to talk to your neighbors, the odds are very good in groups of 3 or 4 that at least one of them will know why you're wrong and can clear up your misconception. Is it as good as having the lecturer intervene with everybody? No. Is it better than traditional lecturing where I just broadcast information and hope it's stuck? Hell yes. Again, more than a full standard deviation. Anybody here from the United States or Canada? Other than myself? Okay. So in those school systems, rough approximation, please don't quote me on this because it's a gross generalization, a standard deviation is roughly the gap between each school year. If you're looking at something like math or language ability, you expect each year to move up about 1 SD from the previous year. Okay? So we can buy you a year by switching teaching technique, and that has been validated in dozens of countries by hundreds of studies, including one done over 4 years by Beth Simon and her colleagues at UC San Diego. Does peer instruction work for introductory programming? Yes. It improves retention. It particularly improves retention among the at-risk who would otherwise drop out. Okay? N is up in the hundreds of subjects. 4-year study, long-term. This is everything we want from science. This is what we should be using in software carpentry. We don't, for 2 reasons. The first is it's very different from what our instructors are used to doing when they teach. And since they only volunteer for us a couple of times a year for a couple of days, that's not enough time for them to become proficient in a new technique. Second, it's not what learners are used to. If we're trying to teach you programming and change the way the classroom is run, you're going to be so confused by the second that you don't learn the first. How many of you use the the Jupyter Notebook? How many of you teach intro programming with it? Don't. I love it as a tool, but for many people, you're now hitting them with 2 stones at the same time. One of them is, here's programming, and the other is, here's this really weird editing interface that isn't like anything you've seen before. And the second gets in the way of the first. You have mastered it, so you forget that there was something there to learn. But you take it into novices, and you're asking them to do 2 things at once. You can't do that. Okay? Please. The question was, does this include students giving feedback on each other's work? Does which include students giving feedback?
Like on peer instruction.
No, and there's an interesting story there. So this is done in chunks of a few minutes at a time. We're arguing with each other about what is the right answer. This is not evaluative. I'm not saying, thank you for your essay, here's some feedback I'd like to give you. Yeah. There was a really interesting piece of work done, coincidentally in Toronto, where I live. Again, how many of you have been in those classes that have hundreds of students in them? Okay. You can't give out essay questions in an intro-psych class with 1,200 students because how are you going to mark it? You have to resort to things like multiple choice questions, but we know that they're not really good at assessing aggregate learning. So there's a professor in Toronto who tried an experiment. Here's what I'm going to do. I'm going to get you all to write 1-page essays. I'm going to have all of those essays graded by the graduate student TAs. I am then also going to take those essays and give those essays to your fellow students after anonymization and get them to grade them. Question, how many of your fellow undergraduates have to grade it in order for their average grade to agree with the TA's grades as often as the TAs agree with each other? Basically, how many undergraduates, when averaged out, equal a TA? The answer is 6. And the interesting thing was that if I get you to do this, your learning outcomes improve because you're not only writing essays, you're reading other people's essays and learning from them about style, content, presentation, and so forth. So this sort of peer grading scales, allows us to do better evaluation, and can be proven to be as effective as what we're doing right now. So he built a software tool that would take the essays, anonymize them, distribute them, and do a little bit of spam filtering. Nell is grinning, right? It's 4:45 on Friday. Nell has to have her peer grading done by 5 o'clock. So what she does is 6, 6, 6, 6, 6, 6, right? Or 3, 4, 3, 4, 3, 4, or something like that. That's really easy to detect, and we can filter those out. It worked. It absolutely worked, and the university shut it down. You're not allowed to do this. Because teaching assistants in Canada are unionized, and you're taking work away from unionized staff. So here we have a teaching technique which is provably better than what we're doing now that gets shut down for non-research reasons. If you're trying to change teaching, this is going to happen to you all the time. Okay? So, the payoff from this paper is when Porter and Simon, again working at UCSD, combined all three of the approaches I've been talking about. Do they cancel each other out? Is there so much overlap that you see no net benefit? Or are they additive? It turns out they're additive. Okay? So here we have research-backed teaching practices that produce better outcomes for similar effort, and all we have to do is change. But as my father is fond of saying, most people would rather fail than change. Okay? Trying to get senior faculty to change their teaching practices, yeah, good luck with that. Okay, so I've been ranting at you now for 45 minutes. So here's what I'm going to do. I'm going to back up and talk a little bit about what goes on in brains when they learn, and then I'm going to give you all an exercise. Okay? Before I do that, though, I'm going to ask you to all stand up, please. Okay? Stretch a little bit. I want to see, arms do that. Okay. As you're stretching, work out those kinks. I know these chairs, the table's the wrong height. Keep stretching. I'm not done. Right? You can stop when I finish the anecdote. So, I'm watching the timer. One of the formative experiences in my teaching career was at the US Navy Academy. I go down there, I'm teaching for an hour, the bell rings for the change of class, and without a word being spoken, a room full of young men and women get up, take off their white uniform jackets, hang them on the chairs, drop, and start doing push-ups. This hasn't happened to me before. I'm a little freaked out. So my question, you can sit down now, my question is, okay, is this mandatory? Do you have like a quota you have to do? And one of the graduate students looks at me and says, no, we're graduate students. The undergrads have quotas. So why are you doing it? Well, it turns out that the same fatigue poisons that accumulate in your muscles when you're exercising accumulate in your brain and impede learning. After 45 to 90 minutes of concentrated attention, most human beings are unable to transfer new information from short-term memory to long-term memory. And you've all been in that class or that meeting. Everything's going well. Yep, we're making good decisions. We're learning things. And then you hit the wall and it's just merble. Right? There's a physical basis for that. If you want to resume learning, what you have to do is clear those fatigue poisons. Caffeine doesn't do it. Okay? If you've got somebody who's, fatigue idiot and you give them caffeine, what you now have is a wide awake idiot. Right? We've all been that person at least once, right? What you have to do is elevate oxygen flow to the brain for a few minutes in order to flush the fatigue poisons. And again, most of you have experienced this. You're working away and it just doesn't make sense and everything's going wrong and you're getting frustrated. So you get up and you go to have a cigarette, get a cup of coffee, take a walk, something like that. And as you're doing that, the idea comes to you. Right? There's a physical basis for that. So when you are teaching, you don't go more than about 45 minutes without giving people an opportunity to flush some of those fatigue poisons out of their brain. What I should have done was get you all to do 3 minutes of yoga. But you're new here. We haven't built that sort of trusting relationship. And, middle-aged men in lycra, very bad. Okay? This is, we believe, why accidentally most universities have evolved a system where every hour the undergrads have to wander from one classroom to another. Because it improves learning outcomes. The act of walking from here across the quad into another room gives you that few minutes to do a reset. If you've got exactly the same class happening where you sit in the same room for 3 hours and it's the lecturer who changes, learning outcomes go down significantly. Feels like all the oxygen's gone from the room. Okay? So keep that in mind. The period you've got in which to convey something complex is capped physiologically by about 45 minutes. 45 to 90, but that's looking at the high end, so aim for 45. Okay? Second thing, what is the single most important number in programming? Anybody? It is not 0, 1, or 42. Okay? What's the most important number in programming? You made noise and eye contact. Never make eye contact with the lecturer.
I heard somebody saying pi.
Pi, wrong. Pi's not really a number. 3 is essentially pi. I'm an engineer. 7? Okay, 7, what's the error bars on 7? 7 plus or minus? 7 plus or minus 2. Hands up if you know why 7 plus or minus 2 is the most important number in programming. All right. As a rough approximation, and those people who do brain studies are about to cringe, as a rough approximation, human memory can be divided into 2 layers. The larger one is called long-term or persistent memory. It's what gives you your personality, your sense of continuity. It's your archive. It's your hard drive. As far as we know, it's unbounded. You will die before it fills up. You can keep learning new things well into your hundreds. It works by pattern matching, and it is slow. It can take hundreds of milliseconds to pull something out of long-term memory and into consciousness. That is not fast enough to keep you alive in a world full of falling rocks and tigers and Cambridge cyclists, as we discovered this morning. So, sitting on top of that, evolution has given you a cache. It's called short-term or working memory. It also works by pattern matching. It's much faster, millisecond time access times, and it's very, very small. The initial estimate in the 1950s was that the average adult could hold about 7 discrete facts straight in working memory for about 10 to 12 seconds before things started to drop out. Modern estimates put the number lower, more like 5. 7 plus or minus 2 was the initial estimate, so that's the number that still gets quoted. Okay. You can see this in many things. How long is a phone number? Well, think about what we used to have to do. Some of you are too young to remember this, but phones used to have these round things on them, and you would move the round thing and it would click. It was called a dial. Is there anybody here who's never actually dialed a phone? Because I get yeah, God, I feel yeah, okay. But think about what used to happen. You used to have to read the phone number out of the book and then come over here and dial it. Turns out, study done in 1920 in the United States, at 7 digits, the average adult could complete the task with well over 95% accuracy. By the time you have 12 digits, completion rate is down to 50%. Because by the time you get to the end, you've forgotten the last couple of digits. Now you have to go back and find it again in the phone book, but the line is now dropped because you were taking too long, and around we go. All over the world, we settled on phone numbers that are about the same length because of physical limits in the human brain that we cannot change. Similar question. I am going to ask, oh, you made eye contact. Okay, how big is a sports team?
Sorry?
How big is a sports team? How many people are on a sports team?
12 for football, 6 volleyball.
Okay, other answers? 12 for football, 6 for volleyball? Okay, it turns out the answer is 6, regardless of the sport. When you have human teams that are larger than about half a dozen, they naturally and almost immediately decompose into smaller groups. If you think about football, you've got forwards and backs. Rugby, the front line and the backs. Right? American football, irrelevant, and I don't care. Right? Hockey, which is of course the perfect sport, 6 people. Right? The basic unit in military organization and hunter-gatherer society, for as far as we have been able to determine, is about half a dozen people, because that's how many you can keep track of at once. You cannot keep track in detail of what 10 or 12 or 15 people are doing. You might think you can, but if you've ever been managed by somebody who has 15 direct reports, you know they're skating over all the details. There's just too much going on. Okay? The same is true in programming. If you take a look at this piece of code and you are on this line, and you have to keep track of the 5 input parameters, the 2 values I'm going to return, the meaning of these 2 loops, and why I'm in 4 conditionals, the technical term for your situation is screwed. You cannot keep all of those random arbitrary facts straight in memory long enough to write or debug the next line of code. And you've all probably created that code. You've certainly all had to deal with it. And this is why we modularize code in the way that we do. We're trying to fit it into something that is fairly small and isn't getting bigger. Almost everything in our programming languages exists in order to compress information, in order to allow us to do abstraction so it'll fit inside our cache. The same is also true of learning. If you throw 50 new ideas at somebody in 50 minutes, you've just wasted 45 minutes. There's too much for them to absorb at once. What you need to do is give them a small number of concepts which are densely connected, and I'm going to come back to the dense connections in a bit, and then reinforce it. That's how learning works. You've loaded cache, you've hit it again to reinforce it, and now transference into long-term memory is much more likely to take place accurately. And then you do it again. Okay? So, those of you who program, which I presume is most people here, you'll be used perhaps to the following cycle. On a small scale, what I do is write a couple of tests, then write a little bit of code that makes the tests pass, and then do a little bit of refactoring. right? That's the core agile cycle, red, green, refactor. What's the next little change I want to make? Okay, let me add a couple of tests, they're failing, good. Okay, now let me make the code changes that make the test pass, good, they're done. Now let me clean up a couple of things, right? That's your inner loop. Your outer loop is, I do that a few times, and then I commit to version control so that I can reconcile with other people who are working on the same code base before we diverge too far. Right? That's your inner and outer loop when you're coding. Your inner and outer loop when you teach are, give you half a dozen new things that are densely connected that you can digest as one lump, reinforce it, and then repeat a few times until I hit my 45 minutes, at which point I give you that oxygen break that your brain so desperately needs, and then I repeat. If you can hit that rhythm, you can do that 5 or 6 times a day, right? 5 or 6 chunks of, call it 45 minutes to an hour, and people will be learning at the end of the day. If you try to push as much information into the lecture as you can, and you repeat that, 3 hours in, they have stopped learning because they're drowning, their brain is full. And you've all been in that situation. Everybody okay with this? Okay, so now you know what the teaching rhythm is supposed to look like. So here's what I want you to do. I want you to take 10 minutes and paper and pen or pencil, crayon, lipstick, blood, whatever it is that you're used to writing in. I want you to jot down what it is that you do when you are explaining to people how a simple for loop in Python works. For item in list, do something. Okay? What does your explanation look like? What are the key concepts that you're going to touch on? Right? Obviously, there's syntax, but there's other things going on. There's a loop variable, there's a collection, there's what else is in play? What are the ideas, and how do they relate to each other? I want you to jot that down, and then I want you to compare it with what your neighbor has written down, and I want you to reconcile. This is a teaching practice called think, pair, share. Step number 1, you all do it in isolation. Step number 2, you compare with partners and reconcile. And then step number 3, I'm going to ask a few people to present theirs. Okay? Go. Okay, now hang on a second. What you were just hearing is a room that is learning. Quite seriously, people learn more during conversation with peers than they do head down in silence by themselves. You know this, and the research bears it out. So when you are teaching, you don't want to hear your voice most of the time. What you want to do is set up that kind of conversational buzz. And if you hear people doing that while they're programming, that's a happy sound. Okay, carry on, please. I'm quite serious. You're listening to the room. Excellent. Thank you. All right. Eeny, meeny, miny, mo. In the back row, you two. Okay? Talk to me about what you have in your model. You're going to teach for loops. Novice programmers, there's a microphone coming just on your left. So if the two of you could tell us, what are your key concepts and how do they relate?
Okay, so there is usually a counter, or let's call it a counter,
Okay?
which will have values across a range or a set of other types of objects and numbers. And the for loop will repeat the operations inside the loop for a number of times that depends on this counter. So it will be equal to the size of the range that the counter takes its values in, or the set.
Okay.
Is there anything else you want?
Okay, like in my explanation, I would have explained a little bit, like write the code down and like one key.
Just the concepts, not the how,
not
but
the
the what.
concept. Okay.
Okay. Any advance on this? Let's pull, please. Yep. So I've got a counter takes values from a range or a sequence, and it repeats the for loop that many times. What else is missing? What was in your explanation of a for loop that isn't already up there as key concepts and relationships?
Mine or
Right behind you. Yep. Yep.
Mine is the same.
Okay, yours is the same. Does anybody have something dramatically different? We've got one over here and then one down here. Okay. So microphone here, back row blue shirt.
Yeah, we both agreed that one of the most important concepts is the action that you do inside.
Okay. Is the action different from or the same as the blob I've currently got written up as for loop?
I didn't really get that one, so maybe.
Okay, so there's the action or the body, maybe, is what's repeated. And it's not the counter that repeats them, but this does get repeated. Okay, so let's clarify that. And then there was one down here as well, please. Yeah, green shirt? Same one? Okay. And one over here, just very quickly, I'll say it. You tell me and then I'll say it.
It's about having a collection of items.
Right, so we've said range or sequence. Maybe we should replace that with the more general notion of a collection. Okay, except collection is not a natural notion. It's a generalization of several things. So a novice is unlikely to understand that. That's something we either have to have explained beforehand or expect to fail. Right? This is, by the way, one of Python's failings, and I'll come back to that in a minute, the fact that we run into this so early on. Okay, so let me wipe this. Okay. Round of applause, please, for all our presenters today, please. Thank you very much. What I just did, by the way, is a common teaching trick. You never want silence in the room while you're doing something that they're just watching. I'm quite serious. You don't want an opportunity for people to lose interest and switch back to Twitter. Let's all look at them. Right, okay. So you always want something to be going on. If I need 5 seconds to clear the whiteboard, have something else happening. Never lose pace. Okay, so I've got a loop variable. I've got a collection, and I've got the body. When I think about a for loop, as an experienced programmer who already understands things fairly deeply, those are the three parts for me. The loop variable takes values from, okay? And it does it in order, okay? The collection, the body gets executed once for each value in the collection. Good so far? Okay. The loop variable changes each time that we execute the body. What other key connections don't I have up there yet? Anything that's absolutely essential to a first introduction. Go.
When it stops.
When it stops. Okay? Takes values from in order. I think it implies that when you've done each value that stops, but you're right, that's not going to be clear. So maybe we need to talk about stopping, or we need to add that gloss. It's not a thing in this diagram, but it's something that has to be in the explanation. Go.
If someone needs to be taught what a for loop is, they probably don't even understand the rationale for why you need it.
Ah.
So I think
Okay, keep going.
an example of an average or a sum, just why it's used. Because to us it's obvious, but if someone doesn't know what a for loop
Okay. That's motivation, which is different from being one of the concepts that's in the idea of a for loop. Why is really important, but this is the what. You're absolutely right, we have to motivate them. All right? Printing a bunch of numbers doesn't motivate anybody, because why would I do that? For each data file, for each image in this directory, create a thumbnail. Works really, really well. It's an authentic task. People have had to do it by hand and they realize it's painful. Oh, right, I'm just, for each of those, do this. Something like that really motivates. Any other key concepts that need to go in? Please, over here. Initialization? Yeah. What needs to be initialized in Python? This is going to get the values out of that. If I was teaching for loops in C or C++, for I equals 0, I less than n, I plus plus crash, right? I have that initialization step. Here, the variable is being created if need be and pulling those values in. It's a simpler conceptual model. Okay? Others? Scope? Okay. Are you going to talk about scope in the first introduction to for loops? Absolutely not. I will hunt you down. I will find where you live, and I will sit on your doorstep, and I will cry, and when your neighbors ask why you're crying, I'll say, it was his fault. He wanted to talk about scope with novices on like the second day. Right? I will shame you publicly. Talk to my former grad students. You think I'm exaggerating. Yeah, there's a lot of reasons why I stopped being a professor. So, look what we've got here. 1, 2, 3, 4, 5, 6, maybe a bit of motivation. This is one chunk. 7 plus or minus 2. This is as far as I'm willing to go before I say, now do a couple of reinforcement exercises. This is called a concept map. The blobs are the things that you think of as the ideas. The arcs are the relationships between them, and you notice that they're labeled. You don't just put in an arrow and say that's related to that, because you haven't helped me. I don't know how they're related. You make the relationships explicit, and then you count. There's 2 here, right? Takes values in order. So call that 1.5 ideas, right? I've just hit the threshold of what I am comfortable teaching as one chunk without reinforcement. And one of the reasons that you draw concept maps when you are prepping lessons, and I want you all to do this as you're prepping lessons, is that if you've got 19 blobs and 35 arrows, your lesson is going to fail. You might draw that for an hours-long lecture, but then you need to get another color pen, which I don't have. So I want you to imagine that my finger is red, and you circle subgraphs and say, this is the first chunk, and then I'll reinforce. Here's the second chunk, and then I'll reinforce. This is telling you when your lesson has gotten too complicated to teach in one go. There are other uses for this. One of the things that I have found, but I have not yet found a study to validate this, so this is personal experience, not research. The order in which I teach is almost never the order in which I drew the concept map originally. What I've got here is a directed graph. I can now traverse this graph in various orders, respecting those arrows. So the order in which the ideas came to me may not be the best order in which to teach them. My experience is that if I start off by doing point form notes, which is I think the technique many of you will use, I am much less likely to rearrange things than if I've got a graph and now I have to pick a path through it. I've separated out the what from the order so that I'm not trying to order things prematurely. You may not get the same kick from that, but I found it has improved my teaching. Okay? Everybody okay with that? Second thing, if you're using point form notes, you're almost always writing down those. You're very rarely writing down the connections. And it turns out that if you want the ideas to stick, you have to make the connections explicit. They have to be first-class citizens in your lesson on a par with the concepts themselves. Because the more connections there are between concepts, the more likely the concepts are to go into long-term memory. The more connections there are between you and a social group, the more likely you are to remain in the social group. It's exactly the same effect. Okay? And I find that when I'm writing down point form notes, I'm almost always writing down the facts. I'm very much less often writing down the connections between the facts, and so those get shortchanged. Okay? Other ways in which you can use this technique. How many of you are in a research group where you collaborate with other people? Okay. When you go home, I want you to do the following exercise. I want you, not that kind of exercise, but thank you. Okay, I want you to do the following. Tell people about concept maps and say, right, we're all now going to take 5 minutes and do a very small concept map of our research project that we're working on, independently. And then we're all going to reveal them at the same time. Your concept map and those of your colleagues will almost certainly look nothing alike. And this is why you're arguing with each other. I do this with many projects. I'm involved in things outside programming. And what you find is that people are using the same words, but their mental picture of what they're doing is quite different. Many of you may have been in that relationship with another human being. Right? It's not a happy relationship. Right? This is a way to externalize cognition. I'm taking what I'm thinking and I'm putting it out here so that you can see it, so now we can point to things and argue and you can say, no, that's not my mental model of this. If you're teaching with other people, doing research with other people, planning a family holiday with other people, yeah, it feels kind of silly to do this if you're planning a family holiday, but on the other hand, the relationship is much more likely to survive if you both go to Italy with the same picture in your head of what the hell you're planning to do. Right? It does not include daily trips to the Uffizi Gallery. Not for me anyway. So, another way you can use this is in class as you are teaching. I tend not to do this, but I have colleagues who do, and I am trying to develop the habit. Draw the concept map as you are going through the lecture. I talk about something and I put up the bubble, and then I talk about something else and I put up the bubble. Then I explain how they're connected and I draw the arc. This reinforces learning because I'm now giving you redundant information that reinforces. There's some brilliant work by Richard Mayer at University of California, Los Angeles, going back to the late 1980s. He has been studying multimedia learning for almost 30 years and has built a predictive cognitive model. Your brain has different channels for processing visual and linguistic information and for storing visual and linguistic information. Different parts of your brain catch it and save it. They can reinforce each other. If when I'm telling you a story, okay, that's linguistic information, I am also giving you something to look at, then when you glance back at this, it will remind you of what I was saying when I drew that bubble. Okay? They help you remember. If I hand you a completed diagram on paper and then I talk, the effect goes away. It doesn't happen. You have to see this emerge so that you've got the sequencing cues, you've got the synchronization. Okay? I do not have the habit of doing this. I'm trying to develop that because the research says it will improve outcomes. Another way in which you can use concept maps in class is to have your students draw them and give them in at the end of the lesson. You glance at those and I promise you, you will instantly see what it is you need to correct or fill in the next lesson, because there will be concept maps that are clearly wrong. They have misunderstood what you think you explained. Getting them to write an essay? Sure, except that takes a lot of time. Getting them to do something on this scale, if they're used to doing it, the first few times it's always hard, but if they're used to doing it, getting this and looking through half a dozen of them, you go, right, nobody understood that. Okay? Nobody got that part of the lesson. I better clear that up after lunch, or I better fill that in tomorrow. Okay? These are ways in which you can use this technique and it will improve your teaching. It's low cost. Okay? And yes, it's not zero cost. It does take time, but there's something I need to reinforce here. Most of us teach at the speed at which we can talk, rather than the speed at which our audience is actually learning. You have all been in a lecture where the lecturer was bound and determined to get through the PowerPoint deck, no matter what. And I have seen people towards the end of a lecture just hold down the advance key so they can have all the slides flash through, and they're talking and there's no learning going on. We want to introduce feedback mechanisms so that we pace our teaching to the speed at which people are actually learning. Number one, it avoids us wasting our time. Number two, it's a clear indication that we care, that we are not indifferent. Remember what I said an hour and 20 minutes ago? Indifference is one of the two great demotivators. As soon as you show your audience that you actually care whether they're learning, they will start learning more. Okay? Getting this kind of feedback is useful. Getting this kind of feedback and then acting on it in ways that they see will dramatically improve learning outcomes. Okay? They will trust you. Everybody okay with this? I do this with co-instructors all the time. We're teaching the same topics in Python or Git or Shell or regular expressions. But before we start teaching, 3 minutes on the whiteboard to say, here's how I see this topic, so here's how I'm going to approach it. And Nell goes, oh my God. Except she doesn't because she's French. What would you say instead? Mon Dieu. Right? Mon Dieu, his accent, make him stop pretending to speak French. No, she would just say, no, that's not how I was going to do it. 3 minutes of this clears it up, and then you both hit the stage playing in the same key. This turns out to be important. Everybody got this? Okay, so when you're designing lessons, this is a big part of what you're going to do. Right? You're going to start drawing out a concept map. What are the big ideas? How do they relate? You're going to show it to somebody to get a reality check. You're going to carve out chunks that look about that big, and then you're going to figure out, what do I do after each chunk? And that's what we're going to do after the break. Okay? This is a reproducible way in which to design lessons. Okay? Everybody okay with that? All right. Back at 3:30. Everybody, I want everybody out of their chair. Switching to Twitter does not count as taking a break because it is not elevating oxygen flow to the brain unless you're really, really angry about something on Wikipedia. And even then, it doesn't help. So everybody, the oxygen's out there, the drinks are out there. We will be back here in 9 minutes. Go. Grab your seats. I want to make your lives better. We live to serve. Okay. How many of you are familiar with the Weikert et al. Result from PLOS One? Okay, how many of you have to review scientific papers? Keep your hand in the air if you look forward to this, if you enjoy it, if this is what brought you into science and you want to keep doing it. You're a very sad man. We will get you some help. Okay. Here's the story. If you publish in an American Psychological Association journal, that author agreement that you sign but don't read says, I promise that I will share my data with people who ask so that they can check my results. Okay? So what Weikert and his colleagues did in 2007 was go through a bunch of papers, 49 papers from 2 APA journals, and contact the authors and say, please may I have your data? And what they published in 2007 was the histogram. How hard is it to get data? And back then, I realize this is 8 years old, which is Paleolithic times for some of you, but back then, roughly a third said, the URL is in the paper, you fool. Roughly a third, if you kidnapped their dog and pulled their teeth, they would give you the data, and roughly a third, they never got the data. So they published that, and everybody said, tisk, tisk, we must do better. And they thought that Weikert's was done. Weikert's was not done. Over the next 3 years, he and his graduate students redid every single statistical analysis in all 49 papers, 1,148 analyses redone with other people's data. If this sounds like hell, I'm sure it was. How many of you are on Twitter? Go take a look at the hashtag other people's data sometime. There are no happy stories there. Okay? What they published in 2011 was a beautiful result. Is there a correlation between how reluctant you are to share your data and how many mistakes there are in your statistics? R is 0.92. It is a straight line. So, the next time a paper lands on your desk for review, the very first thing you do is say, please may I have the data? If they say no or don't respond, you bounce the paper. You say there is a 92% chance that you have borked your statistics, you cite Weikert et al., and you're done. I just made your lives better. You're welcome. Yes, Gail.
And then the editor will override your decision.
Not my problem.
Sorry.
Not my problem. You see, what it did was it gave you a morally defensible reason to spend 5 minutes rejecting a paper. Okay? And it'll happen somewhere between a third and a half of the time. I just made your lives better. Okay? Let's come back. Oh, I've got some maps I'm going to show you eventually, but we're going to get there. All right. Next thing we're going to cover. There's some really nice work going back to the late 1980s on the cognitive changes that occur as people are learning. Okay? You see things differently. You think about things differently when you're an expert than when you're a novice. We all know that, but it turns out we can actually get a handle on it. And there's a 5-stage model that was developed and validated with intensive care nurses that has since been revalidated in several other domains. Okay? Go and see how learning works if you want all of the citations. For our purposes, I'm going to boil it down to a simpler 3-stage model because there's some subtleties in some of the layers that I don't care about. For our purposes, we are going to classify people into one of 3 categories: novice, competent practitioner, and expert. Okay. What is the key difference between a novice and a competent practitioner? When you say somebody's a newbie, they're a novice, what is it that distinguishes them and the way that they think about this problem domain? I'm going to pick on 1, 2, 3. You thought I was over there. No, I'm going to pick on you this time. Yep. What is it that makes a novice a novice?
They have no idea what they know and what they don't know.
They don't know what they don't know. In Rumsfeld's term, unknown unknowns. Okay? They lack a functional mental model of the problem domain. They don't have a map of the terrain. How many of you have ever worked tech support or had to teach an introductory class, and people come in with questions that aren't even wrong because they're fundamental category errors. They don't have the right pieces assembled, so their questions simply don't make sense. Right? You've all dealt with that, right? Does it matter what color the laptop is when I'm trying to install Windows? Well, no, it's funny, except it's not to them. And if you mock them, what you're doing is reinforcing the sense of indifference, and down goes the learning. What they have done is borrow bits and pieces from other mental models in other domains in order to cobble something together for this domain that is solid enough they can stand on it to take the next step. Everybody does this when they are learning all the time. You do it as well. Our goal with novices is absolutely positively not to give them lots of information. In fact, there's some brilliant studies from the early 2000s in physics education showing that if we give people too much information too early, we're actually setting them back because they're going to take that and fit it into their existing incorrect mental model and reinforce the mistakes. If you think of the categories in their mental model as boxes, what we are doing is putting lots of weight into those boxes, and they're now harder to move around. Okay? So, what I would like you all to do, you each need 1 blue and 1 pink, and then pass them on. I want everybody to have sticky notes of both colors. So take them, pass them around, okay? Make sure you got 1 of each. Now, what our job is as instructors when we are teaching novices is to help them form a workable mental model. It does not have to be completely correct. My father taught for 42 years, and when I told him I was going to become a full-time teacher, he had 2 pieces of advice. The first was don't, okay? And the second was never hesitate to sacrifice truth for clarity. Don't drown them in information and details and howevers and accepts. What we've just drawn up here is an incorrect model of a for loop, because where is break? Where is continue? Where is raising exceptions? Where is modifying the collection as we're iterating through it? They don't need to know that yet. They don't need to know that to get from novice to competent. Okay? Everybody okay with this? All right. What's the difference between a competent practitioner and an expert in any domain? If you've got an answer, just raise a hand. What cognitive differences? What's different in their head?
An expert can say the advantages and disadvantages of different ways of doing it.
Okay, can weigh different approaches. Others? What's the difference? When you say somebody's an expert, what do you mean by that?
Well, has lots of, let's say, details we might be using that for the
Okay. Lots of details. Okay. Turns out to not always be true. There are many people who are experts who know less facts than people who are merely competent. How many of you have ever had the misfortune to have a sports trivia nut as a roommate? There are people who know every statistic about Premier League football matches going back to, I don't know, 1895, but can't kick the damn ball themselves. Okay? What else distinguishes the expert? Go.
Well, in the mechanisms and connections instead of facts.
Yep. Connections is the right track. We'll come back to that one. Go. Has made a lot more errors, almost certainly, but that is not what produces expertise. Anybody on this side of the room? Should I stick with the smart side of the room, or do you guys want to get on the field? Okay, please.
But maybe he knows what he don't know.
Knows what they don't know. Okay. It turns out that the key distinction between somebody who is merely competent and somebody who is an expert is in their mental model. Unsurprising. And to explain it, I'm going to have to lie to you. Okay? Now, I'm going to give you an analogy. It is incorrect but useful. I want you to imagine for a minute that your brain stores knowledge as a graph. Facts are nodes, and then there are linkages between them. This is not, absolutely not a picture of how your brain actually stores information, but I want you to pretend that it is. What distinguishes an expert from somebody who's merely competent is that the expert's graph is much more densely connected. They might not actually have more facts, but they have many more linkages between the facts. Why is this important? Well, in order to traverse my mental model of, I don't know, quantum physics, it having been almost 30 years since I did a quantum course, I have to go from A to B to C to D, back to C to D to C to D. That's about as far as I got with quantum, but maybe eventually I'll get to E, F, G, and H. You as an expert are going to have a direct connection from A to H. You're going to do in one step what took me 7. And it looks like magic from the outside. Because for me as somebody who's competent, I don't know how you got from A to H. And neither do you. Experts tend to be really bad at explaining their reasoning because they didn't reason. As far as they're concerned, there is a direct connection from here to here. Why did you go all that way? Oh, right. You don't know as much about this as I do. So I'm going to reverse engineer some sort of path through what I think are the nodes in your mental model, which may or may not have anything to actually do with your mental model, and it's almost certainly not the path you would actually take in order to try to explain what I would have done if I wanted to fill in between A and H, except I didn't think that way. This is called expert blind spot. Experts tend to forget that there was ever something there to learn, which makes them less good instructors for both novices and competent practitioners, because they're just doing it in one step and then trying to figure out what you would have done instead. And it's frustrating as hell when somebody says, oh yeah, you just snargle-flarg the blingle-flam, and they go, what? It's like, it's obvious. The answer is, no, it is not. But it is if you've been doing this a lot. Okay, I'll come back to your question in a second. What does it take to develop expertise? Thousands of hours turns out not to be true. How many of you drive a car? Okay, most of you have probably driven thousands of hours, but are not expert drivers. You know, bombing, you might think you are, particularly if you're from Sicily. Boy, that was scary. So, right, if you have to, you know, skate the car across the frozen lake while James Bond is shooting at you from the helicopter, you're not going to be able to do it, right? You're not expert drivers. There's something else above and beyond the thousands of hours of practice. What is it?
Deliberate practice.
Deliberate practice. You have read ahead. You have read ahead. We've spoken about this, Robin. Okay, everybody point the finger of shame at Robin. There we go. Okay. No. What you have to do is reflect on what you are doing. You have to stop and think about what worked and what didn't. You have to make the mistakes and then think, why didn't this work? As far as we can tell, expertise only emerges as a result of reflective practice in any domain. My daughter is 8 years old. She is learning how to play the piano. And about a year ago, she went through a transition that every music teacher learns to recognize. She went from thinking of it as getting her fingers in the right place at the right time to trying to produce a particular sound. And it is a world of difference. In the first case, it's a mechanical finger exercise, and it's rather painful to listen to. In the second case, there's now a useful feedback loop. She is thinking, if I do this, that sound comes out. If I do that, a better sound comes out, so I'm going to do the second one. She might not even be conscious that this is what she's now doing, but it's a recognized stage in cognitive development. She is reflecting, and now there's that feedback loop, and that's how improvement is going to come about. One of my nephews, for a bunch of reasons we need not go into, has never made that transition. He can play very proficiently, but there's absolutely no beauty in the music. Right? For him, it is still, in his 20s, a mechanical fingering exercise. And I don't think anybody's ever going to pay money to listen to him play piano. Okay? This comes back to what the Japanese refer to as Jugo Kenkyu, what Elizabeth Green was talking about in building a better teacher. It is not enough to go and watch somebody teach. You have to reflect on what was different and why was it different. What made that work or not work? How many of you play a sport seriously? Okay? Okay. I swam for years. I swam for years. And for years, coaches would tell me I was rolling my shoulders. And I would say, no, I'm not. And then one day, and this goes back to the early 1980s, a coach brought in one of those first generation handheld video recorders and filmed me and then made me watch it, and I cried. Because I was doing this. Right? I had absolutely no sense of what was wrong. As soon as I had that feedback, I could fix it. Okay? You need to give your learners feedback in real time or as near as you can manage in order to help guide their learning. They need to know when they're on the right track and when they're failing, and if they're failing, why. It's not just you're wrong, but you're wrong because, and now here's something you can fix. Okay, there was a question here and then a question there. Go.
Yeah, I was wondering earlier, would you then say that the proficient people would be better teachers than the experts?
Absolutely. There are approximately 400 people qualified to teach software carpentry worldwide today. Of those, 3 have degrees in computer science. Our attempts to use computer scientists and professional developers to teach scientists have been, and forgive me if I go off color, an absolute fucking disaster. Because the programmers are in love with programming, and the scientists, by and large, really aren't. I don't know how to break this to you, but you're all really odd. Okay? Because I think most of you are scientists, and you actually like programming for its own sake, or you wouldn't be at a Python conference. Most scientists regard programming as a tax they have to pay in order to do their science. And they are right to do so. They want to be chemists doing chemistry. They don't want to be statisticians, and they don't want to be programmers. So if you give them somebody who's in love with programming and wants to explain how recursion can be implemented on GPUs in the cloud, the answer is, go away. Okay? This happens. Almost all of our instructors are people who are only a couple of steps ahead of the people they're teaching, so they remember the pain and they can relate to the mental model of the people they're teaching. Now, if you've got more time to train your instructors, absolutely you can take experts and make them really good teachers, but they have to recognize that it's going to take as long to develop expertise in teaching as it takes to develop expertise in quantum mechanics or pure functional programming languages. It is a teachable, learnable skill, and it has to be mastered, and just because you can do the thing does not, absolutely positively, does not mean you can teach the thing. Okay? And this is something that most research faculty will adamantly refuse to acknowledge. Over and over again, they will simply dismiss or brush away research done by their peers in education. I've seen it happen time and time again, because if the educational researchers is right, you've been wrong for 30 years and you need to change. And if you've got tenure in a physics department, you ain't going to listen to that from anybody except a mathematician. And even then, you're going to want to check their credentials. Okay? There was a question over here or no? Okay. So, no. Yes. Absolutely. Absolutely. right? And Jimi Hendrix played guitar upside down and backwards without having ever been taught. He picked it up. That says nothing about the other 90% of our species. When we're talking about any research involving human beings, we are talking about a distribution, and there will be outliers, right? There are people who have, through happenstance, turned themselves into really good programmers without ever being taught how to program. They've just picked it up. They are 3 to 5% of the population. I don't care about them. They're going to succeed without our help. I care about the 95%. I care about the everyone else. There are people who are really good teachers. Until you look closely at outcomes, when we say somebody's a really good teacher, what we almost always mean in a formal educational setting is that they are getting high ratings from their students, but we know that does not correlate with learning outcomes. If we go back and take a look at how much of those lectures are retained 2 or 3 years later, and how many of those students are retained in the program, we get a very different picture, right? And that's research that also tends to get brushed aside because nobody wants to tell the Nobel Prize winner that despite the fact that people applaud at the end of all of his lectures, they've learned nothing. I am an entertaining lecturer, but it has taken me 15 years of hard work to be an informative lecturer. Right? And it took me 15 years before that to acknowledge that there was a difference. Okay. So I'm hoping you can all do it in 10 and 10 instead of 15 and 15, right? So in something like software carpentry, our goal is to help people get started in the transition from novice to competent. We explicitly do not care about competent to expert. Okay? We don't because we can't fit it into the 2-day workshops that we run. There's just not enough contact time. And we don't really know how to engineer that transition at scale, and neither does anybody else. Mentoring and one-to-one coaching, and yes, thousands of hours of reflective practice are all parts of becoming an expert. The apprenticeship model through which you learn how to do research by doing a thesis under the direction or at least the benign negligence of a supervisor, right, seems to be intrinsic to developing expertise. So does a lot of practicing and noodling on your own. But that does take a lot of time. So we're going to brush that one aside. We're going to take a look at novice to competent. What we need is a feedback mechanism that we can deploy as the learning is taking place. And in order to explain how we're going to do that, I have to introduce a little bit of terminology. You've all got sticky notes? Where have the sticky notes gone? Okay, no, where did the pile, oh, I can use these. Okay. Software carpentry is actually a sticky notes way of making more sticky notes. So, who does not have sticky notes? Okay, where did the pile get to, or have we run out? We ran out. Okay, we are now going to ignore the 2 front rows of the class. Okay, sorry about that. Okay, I know the difference between formative and summative assessment. What? Okay, formative versus summative. Not clear. Okay, hold them up. Okay, excellent. We do this all the time in software carpentry classes, right? And when we take a look at the feedback, one of the things people take away is not just what we taught about computing, but the fact that we've introduced a real-time feedback mechanism that scales. Here's what I want you to do when you're teaching programming. Everybody gets 2 sticky notes. Things go well. I feel like I'm making progress. I've finished the exercise and I want somebody to check it. Up goes the blue or the green. I need help. I'm lost. Please slow down. Up goes the pink or orange or sometimes yellow, but it's kind of cheap to use the yellow. Okay, so this gives you a real-time status light that is really easy to deploy, and if somebody needs help, they can carry on typing and they don't have to sit there like a dork with their arm in the air. People who are floating in the room to help can just check to see if they're pink sticky notes. This works really well. This is an example of a transferable teaching technique that's easy to deploy, that improves the outcomes and improves the student's appreciation, that lets you focus your energy where it's needed. Okay? Do this. I go through lots of sticky notes because the feedback we get from classes is that they improve outcomes. Okay? You can also use them as a simple voting mechanism. You know, how many people think it's A, how many people think it's B, tea versus coffee, right? So, we need something that will allow us to tell whether the lesson that we just taught has stuck and we can move on, or whether we need to go back and try teaching it again in a different way. There is no point repeating exactly the same words. If my first explanation didn't work, repeating that explanation slower and louder is unlikely to work as well. So I might have to come at for loops a different way, use a different example, traverse the graph in a different order, something. But I need to know whether you're all ready to go on. What's a good thing that we can deploy at scale in a class? Well, my favorite technique is multiple choice questions, MCQs. Okay? Now, at this point, I'm going to back up and explain the difference between formative and summative assessment. And I will type those two words in. I'm not much of a graphic designer. In both of my startups, I was told after a few weeks I was never allowed to work on the user interface again. So I do my slides in Emacs. Okay, and then I pretend that it's cool. Okay? So, summative assessment is summing up at the end of the learning. Has it stuck? Is the learner ready to go on or not? It's the final exam. It's the driver's test. You've done the lessons, and now you get in the car, and somebody takes you out into traffic, and oh my God, stop! And you're not allowed to get your license. Okay? Or maybe your outcomes were happier. Right? So, that's a summing up. We do summative assessment because we have to batch people up. If we could afford one-to-one instruction for every single learner at their own pace, I would just work with you until you're ready to fly on your own. But we can't. At some point, I have to decide whether you know enough about calculus to carry on to the complex analysis course or not. I have to decide whether you're safe to be allowed out on the road driving on your own or not. There has to be some sort of summing up. Okay? Formative assessment is supposed to be quite different. Formative assessment is how we shape the learning as it's going on. It's how we give you feedback while you're learning about what you've learned and whether you're done, and it's how you give me feedback about whether we're ready to move on or whether we need to stay on this topic. Okay? So this is the end, that's the during. The problem is, in adversarial educational systems, which is almost all Western educational systems, formative assessment gets interpreted as summative assessment. Every time there's some sort of a test or a quiz or anything where I get to observe your performance, you will interpret it as summing up. This is something I have to pass, rather than here's an opportunity for the teacher to get feedback on what I've learned so that they can shape the learning. As an example of this, when we run software carpentry workshops, we have a little questionnaire that we send out to people to ask them what they already know. And we say in big, bold letters, we actually used to have it blinking, but I was told to take out the blinking tag because user interface design. It would ask them questions. Can you do this using any programming language at all? Can you do this using the shell? Can you do this using version control? And what we found was even those simple questions, where we advertise that this is to help us shape the learning to their starting point and their pace, we're scaring off a very large number of people. It doesn't matter how often we say to graduate students, this is just to get some information so that we can tailor the lessons. They would all interpret it as an exam they had to pass before they should take the workshop. And if their answers were, I don't know how to do this, they'd go, well, this isn't the class for me. Right? And we're still beset by this. We've tuned that questionnaire several times. It's not quite as off-putting as it used to be, but we still lose people because they don't believe in formative assessment. They only believe it's summative. And this is a barrier that we have to get past. Okay? You have to build a relationship of trust with your coach in order to, or your colleagues, in order to accept their feedback as I'm trying to help you rather than I'm judging you. Right? And if you've coached sports, if you've been a music teacher, right, you've had to work through this and build that trust with people before you can start having some conversations. Okay? So, let's come back to formative assessment. I like using multiple choice questions for formative assessment. Okay. Do I get a fist bump too? Okay. So, he can pass it on to you. So, it's not associative, it's not commutative, it's distributive? No. Transitive, thank you. Transitive fist bumps. It's been a long time since I did math. I like using multiple choice questions for several reasons. Number one, they're fast. What we saw in that little video from India was a multiple choice question. Takes a minute to read and think about, and then you're ready to vote. So if I've taken 5 or 10 minutes to explain for loops, and I want to know if you've all got it, because you already knew it, or because my explanation was crystal clear, or something like that, and we're ready to move on, I'm going to throw up a sample of code and ask you a question about it, and then I'm going to have several possible answers. 4 is a good number, because the question itself is going to take a few slots in short-term memory, and that leaves a few others left over for the right answer, and the answers that are plausible distractors with diagnostic power. And that's a huge mouthful, so I'm going to break it down. When you are giving a multiple choice question, you want there to be one and only one right answer. Right? And you want all of the wrong answers to be plausible. They're called distractors. They're not called wrong answers. They're called distractors. You want them all to be plausible. Okay? They should look like they might be the right answer. If I ask you a math question and the answers are 5, 9, 11, and a fish, ha ha ha, okay? All I've done is annoy you and waste your time, right? The joke isn't funny. Even little kids will look at it and go, that's an adult trying to be funny, just humor them, right? No, you want all of the wrong answers to be plausible, but you want them to have diagnostic power. You want them to give you insight into what it is that the learner has misunderstood. And I'm going to show you what I regard as the most beautiful multiple choice question ever written. Okay. Take a moment. Okay. Those of you in pure math, you may need to take a little bit longer. Joke I heard a while ago, or whatever you want to call it. Physicists care about decimal places, astronomers care about the exponent, the economists are happy if they've got the sign right. So, what is 27 plus 15? Shout it out, please. That was a pathetic shout. Try this again. What's 27 plus 15? Can I have a hallelujah? Thank you. If you are teaching a child multi-digit addition and they say 27 plus 15 is 32, what have they misunderstood? Please, you, sir. What? Okay, be more specific. What's their cognitive error? The carry. Thank you. Okay. They've just thrown away. They've said 7 and 5 is 12. I don't know what to do with the 1, so I'm just going to keep the 2. I'm going to throw away, and then I'm going to do 2 plus 1 is 3. Right? That's a very, very common error. So I'm testing for that specific error. I'm not just making up random numbers. I am probing for a cognitive error that I believe occurs frequently. What if they say 312? What's the mistake? Somebody in the back, please. Cheap seats. What have they done wrong if they say 27 plus 15 is 312? Say it again? They added 7 and 5, they got 12. They know they can't just throw away the 1, but they don't understand they're supposed to carry it into the next column. So 7 and 5 is 12, and I write that down, and then 20 and 10 is 30, and I write that down, and I get this. That occurs in about 5% of kids. Okay? Now, here's the kicker. Here's the one that really persuaded me. If they say 33, what's the cognitive error? What's the bug? I know you know. They've which? They haven't. I hadn't thought of that one. They misread the 5 as a 6. Possible, but there's something else deeper. They've added the carry in. They said 7 and 5 is 12, and they've taken the 1 and added it back into the 1's column. They've taken the 2 digits of 12, and they know they're supposed to add the 1 to something, so they add it into the same column, and then they do the next column. That's about 3% of children. Every single distractor tells you what misconception to correct. All right? And if you give it in bulk, and I'm looking at you all and you've got 4 colors of sticky notes, or you've got cards labeled A, B, C, D, or you're using clickers or anything else where I can get real-time feedback, if you all answer 312, I know what I need to explain next. There's a common misconception that I need to clear up. If you all say 33, I have a different misconception and therefore a different example to use. And if all of you say 42, I say, well done, and we move on to the next topic. We don't need to waste any more time here. If you all give roughly even distribution of roughly a quarter for each answer, then my lesson has failed, and I need to start over again and find a different way to come at it. Okay? This is brilliant in a bunch of ways. Number one, if you're brave, and I'm usually not, but I'm trying to get better, you can do the question before the lesson. How many of you have ever sat through a lecture that was telling you stuff that you and everybody else in the class already knew? Yeah, was it fun? Okay. The first time you have a lecturer get up and say, okay, let's see where we need to start. Here's a question. Good, you've all got that. Here's another question. Good, you've all got that. Here's a third question. 95% of the class has got it. I'm going to keep going. Here's a fourth question. Now we need to start. I'm just going to skip the first half of my slide deck. You just made a room full of friends because you're showing that you're not indifferent. You are pacing the instruction to the particular audience. You're showing that you're caring about them. Motivation goes up, learning goes up. And you're wasting less of your class time, which gives you more time to focus on the things where they actually need the help. You then do this again at the end with a different question, and you can tell, am I ready to go on, or do I need to repeat this? You are teaching at the speed at which they are actually learning, rather than the speed at which you can talk. And again, motivation goes up, learning outcomes go up, because you are focusing your effort where you need to. Everybody okay with this? There are other things you can use beside multiple choice questions, but these are my favorite. Because they scale really well. You can have a room with 600 people, they're showing colored cards, and you can look at it and say, right, here's what I need to do next. Everybody okay with that? Okay. So, let's come back to formative versus summative assessment. I'm now going to tell you how you design a lesson in the large. Okay? Not the little chunks, not the inner loop of what's my next 5 minutes going to look like, but what do I do on the scale of an entire hour? Here's how most of us, untrained, but imitating our own professors, design lessons. Step one, oh crap, class starts next week. What am I teaching? Thermodynamics. Right, what do I know about thermodynamics? Let me start writing that down. And by writing it down, I mean let me Google for other people's PowerPoint decks and start borrowing things, but change the university logo in the bottom. If you didn't know that's how you teach, that's how you teach. Okay, and now it's been 3 weeks, and I promised in the course handout that there would be an assignment. What have I taught you in the last 3 weeks? Let me ask some questions about that. 3 weeks later, crap, time for a midterm. 3 weeks after that, another assignment. And then, oh, there's a final exam. That is typically how we do it, okay? Now let me ask. I know what test-driven development is in coding. New term to me. TDD, what? Okay. Almost everybody knows it. For those who don't, test-driven development is the practice whereby which I code in the following way. Step number one, write some tests that will only pass once I've added the feature or implemented or fixed the bug. Right? I do not start by writing code. I start by writing tests, and then I run them to make sure that they actually fail. Because if I think these tests are not supposed to pass and they do, something's wrong. Step number two, I write the code that makes those tests and only those tests pass. Step number three, I do a bit of cleanup, and then I commit to version control. Okay? People who do this swear by it. The evidence on whether it improves productivity is mixed. I've just got another paper to review yesterday on the subject. But people who use it believe that it helps focus them. Because I don't just wander off and write a whole bunch of code and then go, right, I'm supposed to test this, but oh, look at the time. Right? Instead, I figure out where the goalposts are, I write some tests, and then I satisfy that and only that. There is a technique for designing lessons which is directly analogous. It is called, depending on whose book you read, reverse instructional design or understanding by design. And there's a book with that latter title by Wiggins and McTighe. Don't bother buying it. Because they take 300 pages to say what can be said in 5 minutes. Right? You've all had that textbook too. Okay? Here's the idea. Step number one, when you are designing a new lesson, figure out what the summative assessment at the end is going to be. Write the final exam first. Because if you don't know how to tell whether learning took place or not, you are not yet ready to formulate the lessons. If I don't know how to tell whether you've learned basic thermodynamics, I better not start trying to teach it, because how will I know if the teaching worked? Okay? I need something that I can give you that you will be able to do once you've learned basic thermodynamics that you can't do right now. Okay? Some questions you can answer, some problems you can solve, an experiment you can do with the lab equipment, some code you can debug, whatever it is. I need to figure out how I'm going to do the summative assessment at the end to say yes or no. Step number 2, I figure out what are the formative assessments I'm going to use along the way to prepare you for that summative assessment. How many of you have ever had a question on a final exam for which the course had absolutely positively not prepared you? Okay. How many of you enjoyed that experience? Okay. So now that I know where I'm trying to get you, I go back and say, what are the things you're going to do along the way as practice to prepare you for the final exam and tell you whether you're ready? What are the exercises I'm going to give you? Step number 3, I look at the gap between what I believe you know coming in and what you needed to know in order to do each of those formative assessments, and that's what goes into the lessons. This is test-driven development for teaching. It works better than the forward-going waterfall approach that most of us use. And by works better, I mean for equivalent investment of time, you get better learning outcomes because it's more focused. I've decided where the goalposts are. Now I'm going to practice kicking the ball, and now I'm going to see how do I get you onto the field. Works better than what sport are we playing today? Okay? Everybody okay with this? Okay, so here's your next exercise. You have just finished teaching. Actually, no, let's switch it around. You are about to teach this, and only this. You're going to give people their first introduction to for loops in Python. And then, I'm going to stick to my original plan. I'm sorry. You've just finished teaching this lesson where you've introduced them to for loops in Python. Okay? And only this. 3 concepts, 4 links. And possibly a motivating example. Why a for loop. Okay? You now want a multiple choice question to tell you whether or not they've understood. By which I mean whether or not your teaching has been successful. Don't put the blame on the learner. Right? It's not did they succeed in learning, it's did you succeed in teaching. So, what is the multiple choice question you will use? And this is the key part, what's the diagnostic power of all your distractors? I want you to come up with a question, and typically for for loop, what I suggest is, here's a piece of code, what does it print? Or what's the final value of this variable? Or something like that. And then you need to have 1 right answer and 3 wrong answers. But for each of the wrong answers, each of the distractors, I want you to write down what it tells you about the learner's misconception if they pick that one. Come back to this example. B, C, and D tell us something about what people have misunderstood. They give us insight. So each of your wrong answers, you don't pick at random. You say, if they picked that wrong answer, this is what they've misunderstood. Okay? When you've done this, I want you to compare with your partner. You answer their question, they'll answer yours, but also check their beliefs about diagnostic power. Everybody okay with this? Okay, as soon as you've completed that, put up a blue sticky note. All sticky notes down. So as soon as you've got an MCQ, and you've checked it with your partner, put up a blue sticky note. If you don't have blue sticky notes, well, there are haves and have-nots in all societies. Okay? Everybody ready? Go. Okay. Remember, you're only testing this much about loops. This is their first introduction, so it's really, really simple. Okay? What's the question? What's the right answer? What are the distractors? And what's the diagnostic power of the distractors? So there was a question. There was a question. Is it legal, is it legitimate to put confounding information in the question, i.e. add facts that aren't relevant? The answer is you're calling on a higher level cognitive skill then. Right? You're asking people to sort through information, determine which bits they need before assembling those bits into a solution. So you don't do that at first encounter. Right? You absolutely don't do that at first encounter, but you might build towards that. Okay? Carry on, please. Okay. All right, hands up, hands on. Okay. No, not hands up, hands up. Wait. Yes, okay. What are the biggest misconceptions when you're teaching for loops? What do people get wrong? What have you seen go wrong when you're teaching a for loop? Anybody? Go, one.
They don't understand the difference between the current item of the list and the list as a whole.
Okay, so confusion between it's working on one element of and it's working on the whole thing. What's another misconception? What else have you seen go wrong when people are working with for loops? Talk to me about that.
Like the indices that you use or the variable that you use to name each part of the collection.
Okay, so what goes wrong with that?
So they just think that that's what you're printing instead of the portion of the collection.
Okay, so they don't understand the connection between the variable and the value. What's another one? They confuse the index, 0, 1, 2, 3, 4, with the element. Particularly if they're coming from other programming languages, they will often think, oh, I is going to be 0, 1, 2, 3, 4, rather than I'm getting the values out, because they've been trained to think that way. What else?
The order.
The order?
They don't realize that it goes through the list.
Have you actually seen that go wrong?
Yes.
Okay. Please.
The loop stops after the last element is proceeded, and not before that.
The list goes through the whole, the loop goes through the whole thing. It stops after the last element is processed. What else? Okay, this is the, okay, one more here.
You often lose range, and they not when they start in 0 and have the last one missing. That's a big thing by range.
So if we're using range, the fact that we count from 0 and the last value is missing, I would absolutely not use that when I'm introducing for loops. And this is one of the big mistakes in Python's design. A very common thing to do in a loop is do this 10 times. That's hard to express in Python because you have to introduce the range function and the fact that we count from 0 and a whole bunch of other things before you can do the trivial case. Okay? What other misconceptions have you seen? Many people will assume that only the first statement under the word for is in the loop, even if they're all indented. Right? They assume that for applies. In many cases, it's because our first examples have a one-line body. So they infer from that that for loops have a one-line body. What else? Okay, this is the point of the exercise. It is forcing you, as somebody who understands it, to consciously re-look at it with beginner's eyes. You all suffer from expert blind spot because I'm assuming you all know how to write for loops in Python, and you've been doing it often enough that it now seems natural to you. I have to tell you, iteration in programming languages is hideously unnatural, right? You know, it is the dead rising from the grave. It is, you know, eclipse at noon kind of unnatural. This is not how people think, right? Beg pardon? We use NumPy instead, okay? So, which is unnatural but in different ways. So, okay, what this exercise is forcing you to do is not just come up with an assessment, but step back and think about how are my learners going to see this? What does it look like through beginners' eyes? Nell.
So I have a question, which is a bit related to some of the things I've seen in some of the software commentary I've been to, which is how do we do this? Because in my experience, when we teach to complete beginners, which happen quite often, we just don't understand what is wrong.
Yes.
You know, it's like we
Brilliant.
don't understand like I equals 1. We
Yep.
don't understand this.
Okay, so one of the things that didn't come up when we were talking about concept maps is that every concept map that you can actually draw is incomplete. I can't explain what a loop variable is without explaining what a variable is. I can't explain that it takes on values without some notion of assignment, and so forth and so on. every concept map is going to assume that there's other things you've taught before. Okay? Now, at some point, you just have to say, I think they know what 3 is. So if I say I is assigned 3, all I have to explain is assignment. I don't have to explain 3, unless they're a mathematician. Right? So, what I'm trying to get you to do is think about your experience and to talk to each other about what have you seen go wrong. So it's defensive teaching in the same way that putting lots of assert statements in code is defensive programming. You anticipate the errors and you try to put in safeguards to catch them as soon as they occur, rather than waiting until well after the fact and then going, well, this blew up, what went wrong?
But my point is basically what I learned what could go wrong by teaching and seeing students do things I did not expect.
Jugyo Kenkyu, you have to talk to other people who've taught this and say, okay, I'm about to teach NumPy for the first time. Please can somebody tell me what they've seen go wrong? Not just share your lessons, but tell me the mistakes those lessons are there to prevent, the things you're trying to diagnose, the stories that work and the stories that don't, the motivating examples that work for particular audiences. Okay? We've got a little over 30 minutes. I have to wrap up at 5 o'clock. So did anybody come up with an MCQ they want to share? Because then I've got a few other things I need to share before we go. Has anybody got a good multiple choice question? Okay. Then here's your challenge. Gail, raise your hand.
Which one?
Doesn't... Never mind. Okay. Jesus, you give somebody a doctorate and they think they're qualified to do comedy. Okay. So, by the end of the day tomorrow, which I believe is Friday, you will all have brought your for-loop multiple choice questions to Gail. You will mail them to him, and he will assemble them. Yeah, absolutely. You will just copy and paste that into a wiki page or something. Absolutely. You just volunteered by being a smartass. Okay? This is what we mean when we talk about community. If you want to build something in Django, you can go to Stack Overflow and ask questions. There are user groups, there are forums, there are lists where you can go, and there's a community that might be snarky, but will help you, right? Hands up if you've never had online help from a stranger about Python. All right. Now, hands up if you have had online help from a stranger about teaching a particular lesson related to Python. Why the hell not? I am baffled and angered by the difference in those two answers. All right? So, we've got to wrap up. So, I want you to send your multiple choice questions to Gail so that he can assemble them someplace on the SciPy website or something. Or you can delegate. Man, you can delegate. You can forward these to somebody else. Nobody make eye contact with Gail. Okay? But what I want is I want you to have a chance to look at what other people think the misconceptions are going to be so that you can borrow their ideas and share yours with them in the same way that you do with your code and in the same way you do with your scientific research, because isn't that what open means? We all get better by helping each other. Okay? At this point, I'm going to rant for a couple of minutes. You think I've been ranting so far? Okay. Hands up if you've ever edited a Wikipedia article. Keep your hand in the air if you think that was a weird science fiction, unnatural thing to do. No, not anymore. Right? Millions of people have contributed to Wikipedia. And yes, some of those articles are perhaps not of the highest quality, but an enormous number have had dozens or hundreds of contributors and are beautifully written. Go and take a look at the Wikipedia article on the causes of the American Revolution. It's beautifully written, it's chock full of useful facts, and it's had over 300 contributors, last time I checked. Okay? Hands up if you've ever contributed a patch to an open source software project. Okay, did you regard that as a strange and unnatural thing to do? Was your immortal soul put in peril? No. Probably not. At least not the second. First time you did it, right. But now, there are a large number of people who regard that as more or less normal. Okay, Hands up if anybody has ever sent you a pull request with a change to your PowerPoint slides. In fact, it's such a funny idea that some of you laugh. A hand goes up, right? One. And change to a lesson, right? Why not? I do not understand. I fundamentally do not understand why the people who contribute to Wikipedia, high school teachers in the United States, are 40 times more likely than the average citizen to contribute to Wikipedia, right? And yet they don't contribute to each other's lessons. There have been lots of attempts to create a Lessonopedia or a Courseopedia, and they've all failed because people don't contribute. Why not? Right now, today, Thursday, out there in England, there are hundreds of school teachers prepping what is essentially exactly the same lesson on how to refactor polynomials. And last year at this time, there were hundreds of teachers prepping that same lesson and not sharing them with each other. And that is idiotic. We can't afford that as a species. And yet those same people are contributing to Wikipedia. If they're programmers, they are contributing to open source software. Why does the practice not transfer to the collaborative construction of lessons? I don't get it. I have heard lots of explanations, and those of you who've suffered through previous talks by me will know that I've been asking this question now for almost 3 years. My standing offer is, if you can come up with an explanation that you can validate, not just an opinion, right, but something that you can validate, I will buy you dinner at the restaurant of your choice. And I realize that's going to be an expensive proposition, particularly if you live in Paris, right, or Tokyo. But I want to know why something which is normal in 2 fields isn't normal in a third. Teachers have a strong sense of community, particularly public school teachers. They know each other. Teachers in the parochial religious schools, they know each other. There's a strong bond. University lecturers know each other. They're teaching the same things, right? But they are not sharing their lessons. And before I get to Nell, let me go to softwarecarpentry.org, lessons.html. Assuming the network connection, there we go. Okay. Our lessons, the source for our lessons are up on GitHub. Our lesson on Git has had 54 contributors so far this year. Our lesson on the shell has had 58. All right? People are treating them the same way they treat open source software libraries. Most of the pull requests are very small. A handful are large, and each of those lessons has a couple of people who are the maintainers, and that's directly modeled on maintainers for open source software packages. You are the one who's shepherding through the pull requests, deciding what to merge, what to bounce, doing some of the review, encouraging other people to do review. And it's working. Okay? It is working. The model, the social model of open source collaborative development that we see on Wikipedia, that we see in open source software development, does transfer to lessons. So if you take a second thing away from this afternoon, number 1 was buy the book. Number 2, we should be doing this at scale. We cannot afford, as a species, to waste time having hundreds or thousands of people building what is essentially the same lesson over and over again, and we shouldn't. How many of you write your own PayPal fulfillment module for Django? Right? There are half a dozen out there, but only half a dozen. I don't expect there will ever be one lesson on how to refactor polynomials because there are different audiences. I certainly don't expect one lesson on the causes of the French Revolution because there are legitimate differences of opinion among different teachers about why it happened and about what to emphasize for different audiences. But there should not be as many Django PayPal fulfillment modules as there are Django programmers. That's nuts. And when we have a junior programmer who insists on writing all of her own code and not using libraries, we tell her she's wrong. Why do we accept that with lessons? I believe very, very strongly that the long-term impact of software carpentry is not just going to be better programming skills among scientists. It's not just going to be that we've transferred better teaching practices. It's going to be that we've encouraged collaborative development of lessons. And that is something that applies to much more than just programming. That, of all 3, is the one that I think we need most to transfer, because then we're as smart as all of us together. One question and then a question. Nell, please. Yep.
So I'm thinking about the SciPy lecture notes
Yep.
that originated here at EuroSciPy,
Yep.
people building together tutorials in courses. And so there's a sprint tomorrow if you want to contribute.
Right, absolutely, right? Treat it exactly the way you treat open source software. Most of the contributions will be little things. And if you take a look at the distribution of pull request sizes, we see exactly the long tail distribution. There's a handful of people who are doing the bulk of the work, and then lots of people making little fixes and improvements, and that works.
But I think there's also a problem, which we also see in software, which is some people are just reluctant in sharing their slides or course.
Mm-hmm.
And this is exactly the same thing as software. I work in one company, and we rebuilt the software from scratch, and we were not going to open source it.
Yeah. I am old enough. I'm 52. Okay. I am old enough to remember when the GNU Manifesto, the Free Software Manifesto, was published. And I remember explaining to people why this free software thing was never going to work. Okay? And I was not alone in that. Most people didn't believe that that fundamental shift that would ever take place, that programmers would ever give away stuff. And yet, here we are. And most software is still closed source. Right? But you can see the numbers changing year by year. And you can see people's attitudes changing year by year. It's a generational shift. You know, I don't think we're even halfway through that change yet. It's going to be another 25 years. But that's okay. Social change always takes time. All we have to do is keep pushing and then see where and when we can take a model that's working and transfer it to other places so it will work there, so the two can support and reinforce each other. I believe that teachers who do open with their lessons are more likely to produce people who do open with their software, who do open with their artistic content, and so forth. Right? We push on all fronts together and we all do better. Go, please.
Yeah, I noticed the contradiction between what you just said about all these teachers sitting there making their own lesson again, and a while ago when you mentioned that real teaching happens that you just copy some slides and change the logo. So which one, do you have any numbers on which one's which?
I was exaggerating for comedic effect when I said everybody copies slides and changes the logo. Unless it is 2 hours until you have to deliver the lecture, in which case anything goes. Right? But no, there's a lot of people out there who are... Let me ask, how many of you have ever made up an introductory lecture on Python? Okay, I'm sorry, but there's a fundamental mistake happening if more than 2 or 3 hands go up in a room this size. Right? Because if I said, how many of you have ever built a numerical algebra library from scratch for Python, and half the hands in the room went up, I would think that as a community we had failed. Right? How many of you have ever used NumPy? Bingo, yes, absolutely. How many of you have ever tweaked it, fixed it, built stuff on top? Absolutely. But written it from scratch and half the hands go up? It's wrong. Okay.
You don't want answers to your question unless I can prove them. So this is not going to be an answer. It's going to be a comment from somebody who's been trying to foster both open source development and maybe some teaching. Not at the same level than you for teaching, but for open source development, trying to do this well. And over the years, I mean, what I've noticed is that basically you have, if you have thousands of users, you have a tiny percentage of people who are going to contribute. Whatever you do, that percentage is going to vary across communities, but it's funny. I mean, you're talking about, or like I think the numbers are worse than this. Like maybe you're going to have 1 in 1,000, 1 in 10,000, maybe even less. And so your pool, when you're talking to teachers, your pool of potential contributors or / users and potential contributors is small. Add on top of this a generational problem and a cultural problem, which, by the way, can be addressed, and you are trying to address by doing this. But I guess that's the real answer. And so what I'm trying to say here, and you probably know all this, is that it shouldn't be, you said it would be a rant, and it's not actually a rant, but it shouldn't be a rant. Part of this is impossible to change.
If you had told me in 1980 that the president of the Conservative Party of Canada would be Grand Marshal in a gay pride parade in my lifetime, I would have told you you were crazy. It's possible. If you had told me in 1985 that a bunch of scientists would voluntarily gather to discuss an open source programming language that isn't actually owned by anybody, to which many of them have contributed, I would have just laughed. Okay? Yes, it takes a long time. But look at all the fights we have won. How many of you have published in an open access journal like PLOS? Okay? That was science fiction when I was your age. It did not exist, and it wasn't going to, until all of a sudden it's already happened, and now we're arguing about the details of green versus gold and exactly what license do we slap on things. Right?
But I think something that hasn't changed is the percentage of people.
But I'm okay with that. How many of you are politically active? I mean, I presume most of you have strong opinions, but how many of you actually get out and campaign? You go door to door and knock on the doors, you help stuff the envelopes. We figure if we can get 5% of the people with strong opinions to send us a little bit of money every year, we're doing well. If we can get 5% of those to turn out, we're doing really well. Okay, that's just the reality. And yet we can engineer social change with those small numbers. Okay? The key thing is pulling in the same direction. A small number of people who've got the same goal can accomplish miracles. I am teaching you a handful, just a small handful of better teaching practices, because these are the ones that I think are going to be easy to adopt. And if you're going to go back to your institutions and try to change things, I want you to all be telling the same story and pulling in the same direction so you don't confuse those crufty older professors who would otherwise say, well, you can't agree amongst yourselves, so I'm going to ignore all of you. We teach a very small number of topics in a software carpentry workshop, partly because we only have a little bit of time, but partly because we want people to go back to their labs and say, all right, I'm only asking you to start writing shell scripts, start putting functions into your code, and start using version control. I'm only asking for 3 things, and you're getting the same story from everybody. You're much more likely to implement. If we try to change too many things at once, the usual result is that nothing changes. Okay? So we have whittled down to get to something small and achievable. Software carpentry is a pale shadow of what I think we need. But it's an achievable goal. And we've demonstrated that. Okay? Changing teaching practices to get you to open source your lessons and collaborate with each other on them in the way that you collaborate on code, that's not a huge change from my point of view. But it's a pretty big one from your institution's point of view. How many of you know how many of you actually teach at your own institution? Okay, who owns the lessons you write when you are teaching at your institution? Do you know?
Well, the copyright is for my company, but I think the release them under Creative Commons.
Okay. Anybody else? Are you sure you know who owns your lessons?
The university of my lessons. I could actually ask somebody.
Okay. At the University of Toronto, it's not clear. There are 3 intellectual property policies at the University of Toronto. Why? Can't get a clear answer on that one either. Okay? So there are lots of obstacles in the way, but we can do this. We've already succeeded to an extent I would not have believed possible with open source software. Right. You are all living in a science fiction universe from the point of view of me at the age of 25. Right? You don't have the flying cars, but you've got robust open source software that you can actually open up and look at. Weren't true when I was your age. Okay, got a couple other things I need to do because we're going to wrap up by 5. Okay? Let's talk a little bit about what software carpentry is. Okay. Software Carpentry is an international volunteer organization. We run 2-day workshops where we try to teach people 3 core things. Number 1, the Unix shell. Number 2, Git and GitHub. Number 3, either Python or R or MATLAB, except I've just lied to you. What we're really trying to teach them is how to automate repetitive tasks, how to collaborate with colleagues, and how to build code that is testable, readable, and reusable. And then, in fact, those 3 are the same thing. If we advertise a course on those big principles, nobody will show up. Nobody believes that big principles are going to help them meet next Thursday's deadline. But if we say, here's the Unix shell, which, by the way, you need to use if you're going to be using the cloud computing resource. Here's version control, because you've all heard of GitHub. And here is a programming language like Python or R or MATLAB. Then they'll show up, and then we can teach them the principle that we want in the context of a skill they believe they need to know. The technical term for this in marketing is bait and switch. I advertise X and then I sell you Y. We do it all the time, and I'm completely unashamed. Okay? So what does it look like to do what we do? Well, those are our lessons. Right? You can go and take a look at the rendered GitHub Pages site, or you can go and grab the source from the repository. We do them in Markdown. Okay. This map, I'm sorry, zoomed in a little too fast. This is where we've been in the last 4 years. Okay. Last year, calendar 2014, we ran 150 workshops for 8,000 people in 22 countries. Okay. We did that with a full-time staff of 1.5 people and a whole lot of volunteers. This is where our volunteer instructors are located. Okay? These are the people who teach for us. And if I expand one notch, of course, Australia gets dropped off the map, and they get really upset about that. And New Zealand, too. Like, there's an entire website devoted to maps of the world that have left out New Zealand. So, what does it mean to teach software carpentry? Well, we put you through a 2-day training course, the extended version of what I've tried to cram into this afternoon, with a lot more time for exercises and practice and talking to your colleagues. Okay? After that, it's a couple of wrap-up exercises, and we certify you, and then you go on to the mailing list. When new workshops come up, when, for example, University of Helsinki contacts us and says, you know, we'd like to have some of this software carpentry stuff, then we will send out a shout to people who are within reach of Helsinki and say, are you available on these dates? And there's the usual three-cornered dance until we figure out dates that will work for the instructors and for the institution. We can match them up, and away we go. Our instructors are volunteers. They do not get paid for their time. But the host institution covers all of their travel and accommodation expenses so that they are not out of pocket. So why would you volunteer? Why would you join the ranks of these 400-odd people? There are several reasons why it's in your interest to do this. Number one, you're making the world a better place. I think we all believe better computing is better science. Number two, it's a chance for you to join a community of people who are really helpful and supportive and friendly in the way that most open source communities are helpful and supportive and friendly, except Linux. Okay? Not that I'm bitter or anything. Reason number three, it's a good way to learn these skills yourselves. Teaching something is a good way to learn it. Number four, and probably the most important one, it's really, really good for your career. How many of you are contemplating an academic career? You want to be a professor one day. Okay, do you know what the academic job market looks like right now? It's awful. Okay, so the first job you have when you want to get a tenure stream position is to get out of the stack of 300 CVs and into the stack of 20 that somebody's actually going to look at. I promise you, if you show up at the University of Arizona and teach a 2-day workshop to the biology department on computing skills, and then say, by the way, I noticed you've got a position on offer, you're in the stack of 20 because you've just shown them that you're useful, that you have skills that are scarce and valuable. Now, after that is research fit and two-body problem and a whole bunch of other things. But we can get you the interview, and that's happened over and over again. How many of you are in academia but contemplating an exit to some other kind of career path? Okay. You go and teach software carpentry, and again, you have demonstrated not just that you've got skills that are scarce, but that you've got initiative. It's a great way to introduce yourself to companies. And again, we have lots of examples of people who've gone from being instructors to, I want to go and do something else. We will help you learn the skills and demonstrate them in a way that potential employers can digest. It's not just your word for it. We stuck a badge on your forehead saying, yes, you actually know enough about this to teach version control, and we trust you to write code. Okay. This has created a virtuous circle, because if it's in your interest to teach, then you'll come back and teach and help us improve the lessons. And as our stuff gets better and we've got more instructors, we can reach more institutions, and around we go. Eventually it peters out, right? In 20 years, I hope that software carpentry will no longer need to exist because this stuff will be normal. It'll be part of people's training. But 20 years is a long time off. Now, why is it going to take that long, and why isn't it already normal? Well, everybody that I run into believes that there ought to be more training in practical computing in undergraduate degrees in science and engineering. People need to know this stuff. Nobody can agree on what to take out of the existing curriculum to make room. There's this many hours in an undergrad degree. The curriculum is full. Right? Every one of those hours is spoken for. And if we want to put in another course on computing, we have to convince the chemistry department to drop thermodynamics or quantum mechanics or organic chemistry or something else that they think of as core to their discipline and that has passionate, entrenched defenders already on the curriculum committee. In the 1990s, over 100 computational physics undergraduate programs started up in the United States and Canada. A decade later, there were only a handful left because they just couldn't force their way into the curriculum and then defend their turf. This is one of the reasons why we focus on teaching graduate students. Number one, grad students have enough time to actually learn things. When you're a faculty member, you have no time to learn. Okay? But more importantly, we want to recapitulate an incident from the history of science. Prior to the 1960s, no Tier 1 university in the United States that I've been able to find taught statistics to people in the life sciences or medicine. Just wasn't a thing. By the 1970s, all of the top research universities had that stats for biologists course that many of you have probably bumped into. Why did it happen then? Why the 1960s? Why not the decade before or the decade after? The answer is the generation that had encountered statistics during the Second World War in the United States, typically working for the US Navy, had then aged up to the point where they were tenured profs sitting on the curriculum committee. They all got the same ideas at the same time, and 20 years later, they're finally chairs of departments, sitting on curriculum committees, signing off on grants, and they can change the system. They saw stats and operations research in the 40s. In the 50s, they've got tenure. In the 60s, they can effect change. We're halfway through that cycle now. Some of the grad students that we were teaching in the late 90s and early 2000s are now faculty. Another 10 years from now, there will be enough that we've trained now in positions of power that they will then be able to say, right, this is what we're going to change in the chemistry department at our university to make room for more computing. And this is one of the reasons why I tie this to better teaching practices. If you can demonstrate that you're a more effective teacher, you will be given the power to go and change the curriculum, and that's where we get the computing into normal teaching. Okay? This is my plan for global domination. And it's working. And you can be part of it. Okay? Why do I care about this stuff? Well, I care about this stuff because I've got an 8-year-old who is going to inherit a planet that is broken in a lot of very important ways. By the time my daughter is a grown-up, we will no longer be able to pretend that we're able to ignore climate change, drug-resistant diseases, resource depletion, a whole host of problems that my generation was too lazy and self-centered to fix when it would have been cheap to do so. You know, we've known about this for a long time, and we have gone, la, 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 I can't hear you. The only things that are going to make the planet livable for the next generation are more science and more courage. I'm trying to help with the former because I want a livable planet 20 or 30 years from now. Not for me, but for you and for my daughter. And we're not going to get there by doing things the way we've been doing them. We can't afford to keep being bad teachers. We certainly can't afford to keep being bad scientists. And it is fundamentally hypocritical of us to say, I want you to pay attention to research on climate change, but I'm going to ignore all the research that's been done on education and learning. Right? Not allowed to do that. So, better teaching is possible. Go and grab How Learning Works. It'll tell you what we need to do. Pick out the pieces that you think you can implement. Start collaborating on lessons. You've all learned the techniques. You all know how to do open. Apply it to the lessons, and 10 years from now, you will look around and say, oh, gosh, who would have imagined? Right? And it's kind of cool when that happens. It also gives you gray hair, right? And, you know, repetitive strain injury in your wrist from answering all of the emails and so forth. But I think that's a small price for you to pay. Okay? We've got 6 minutes. Floor is open to questions, and then I'm going to have to boot out. One.
So, yeah, I completely agree with nearly everything you said, and the teaching, the sort of ideas for going ahead with teaching and so on. How do you actually practically get doing those within, for example, an undergraduate curriculum?
Absolutely. How do you actually do them practically in an undergraduate curriculum? Step number 1, You just go ahead and do it. Gerard Gorman at Imperial College has adopted some of our curriculum, but more importantly, some of our teaching practices, and just started doing them in one of their undergrad physics courses. Right? If you're teaching, most people will just ignore how you teach as long as people are passing the course. So just go try them out. Number 2, never teach alone. Right? Never teach alone. Find somebody else that you can cooperate with. You sit in on their classes, they sit in on yours. You share development of the lesson. Right? You talk to each other about ideas. Right? Over and over again, we've seen with open source and with other kinds of volunteer communities that having a partner there locally that you can go and have a cup of tea with every once in a while and, talk to about the sorry state of the world makes a huge difference to follow through. Again, how many of you exercise regularly? Okay, do you have an exercise partner? Okay. The only times in my life when I've stuck to an exercise regime was when I had somebody to go do it with. We kept each other honest, right? Or there's a class, or there's something, there's some structure to it. Turns out to make a big difference. So you just go ahead and try small things, okay? Other questions? Please.
How do you handle genius in a group? So if there's people who don't follow, like you said something 95%, and they know it, you go on.
What do you do if you've got a handful of stragglers? There's a book by Judith Viorst that I really enjoyed called Necessary Losses. Look, no matter how well you teach and how hard you work, some people are going to fail. It doesn't matter what your teaching technique is. If you slow down to the pace of the 5%, you are essentially failing the 95%. At some point, you just have to accept, as doctors do, that we can't save everybody. Where do you draw the line? I don't know. If 5% are falling behind, I'd probably accept that. If 50% have fallen behind, no, I'm going to double back. What do you do when you have a class of very mixed abilities? The answer is pair programming. Here's an interesting thought experiment. Suppose you've got a room full of people like this, and you're going to put them into groups of 4 to work on a project together. And you know their grades coming into the class, so you can roughly sort them by prior ability. Options for putting them in groups are, number 1, let them self-select the groups. Number 2, do it at random. Number 3, take the top 4, then the next 4, then the next 4, so you're striping. Option 4, stride through. Take an A, a B, a C, and a D. That's one group. Take another A, another B, another C, another D. That's the second group. Which of those 4 approaches consistently produces the best outcome for everybody at all levels? Option A is self-select. That is actually the worst possible outcome of the 4. Okay? Okay. Option B is random. Okay. How many people think it's B? Random selection outperforms all of the strategies. Okay. Option C is striping. Put people of comparable ability together. No. Option D, you want as diverse a range of abilities in each group as possible. Why? Well, if I've got an A, a B, a C, and a D in each group, the C's and the D's are getting coaching from the A's and the B's, and the A's and the B's are learning from teaching the weaker people in their group. If you put 4 A's together, they're all going to be fighting for dominance, and they're not going to learn from each other. If you put 4 D's together, they're all going to be lost together. The more diverse the group, the better the improvement in everybody's outcomes. So, if you've got a class with mixed ability, you flatter the ones who are otherwise going to be bored and say, look, we're going to match you all up, and I want you two to sit together and pair program for a while, but he's the only one allowed to touch the keyboard. Knowledge transfer occurs, and you learn things from doing externalized cognition, from having to explain your thinking, and from seeing mistakes that drive you in directions that you otherwise wouldn't have thought of. Okay? That's a good way to handle a mixed ability course. Question, please.
Is the same true for motivation?
I don't understand the question.
Well, if you have very mixed motivation.
I don't know. That's an interesting question, and I will go and look for that. I hadn't thought of that one. See, this is why I teach. I learn something every time I teach this class. I'm quite serious. That question had not occurred to me, and as soon as you say it, I could make arguments either way. I don't know. The study must have been done. Okay? Other questions? Please.
I've seen a trend at UCL where I work at least, where people are starting to teach software in flipped classrooms, and it's went quite well, and I was surprised.
In flipped classrooms?
Yes, students are given the materials before the classroom, and the classroom is more like a conversation with the teacher about the content, and I was surprised it was successful, because if I was a student, maybe I could be lazy to teach myself earlier before the class.
Mm-hmm.
Do you think that kind of thing would work in software carpentry?
It has not worked for us because our classes are not required And there is no way that you can fail a software carpentry class. So real life gets in the way. Flipped classrooms do work when it's part of the standard curriculum and you're going to be evaluated, because then self-defense kicks in. I have to learn this or I'm going to fail my degree. The evidence we have is that there are two meanings of flipped classroom. And the practice where you watch all of the videos and then we come in and we devote the class to working through exercises works much better than the reverse, where the classroom is devoted to lecture and you have to do the exercises, the application, on your own without somebody there to talk to. Okay? So flipping that around works better, even if you keep the total number of hours put in by the student constant. And early studies of flipped classroom were bogus because students were putting in more hours. They were essentially getting lecture and practical and the videos, so they're adding 2 or 3 hours per class to the load. Of course outcomes are going to go up. More recent studies have controlled for investment of time by students. What I have not yet seen is a study that controls for investment of time by the teacher. How many of you have ever made a set of video lectures to share with people? Oh my God, it's painful. Right? I think it takes me 6 hours to prep a 1-hour talk for an intro programming class. It takes me 30 to 40 hours to prepare a 1-hour video. Video editing is just a lot more painful. And it's not the editing that kills you, it's the revision. If you've got a PowerPoint deck or an HTML page or something like that and you notice a typo, you go in and you fix it. Right? Re-export to PDF, upload, you're done. If you notice a glitch in the middle of a video, nothing takes less than an hour to fix. Right? Just as one example, your voice will sound different when you re-record that 5-second snippet. And it's a little weird to have the voice jump around like that. It's really distracting. Right? So we still don't know how to build good video lessons cheaply. So the study I'm looking for but have not yet found is one that says if the instructor puts in this many hours, right, and we keep that constant, what's the outcome? One more question, please. Go, please.
How does your experience in teaching affect your own learning of new things?
How does my experience of teaching affect my own learning of new things? I am much less patient with bad teaching than I was before I knew the difference between good and bad. In the same way that I think many of you are much less patient of bad code written by your colleagues than you were when you were also writing bad code. Right? And being dropped into a software development team a few years ago, which had decided that, well, version control really doesn't add a lot of value. Yeah. It's difficult to drink Canadian wine after you've lived in France. Okay? Nella's laughing at me because there are actually some fairly drinkable Canadian wines if you have sufficiently low standards. Anyway. Okay. Here's what I want you to do. I want you to go to the Software Carpentry website, and I want you to take a look and see where Become an Instructor is. And there's a little form you can fill in, and that'll get you in the queue. We are going to restart online instructor training. We've taken a break of 5 months while we rethink things. We're going to do a couple of pilots this fall, but starting again in January, we're going to scale this up. Okay? We've had to rethink it because what we were doing wasn't sustainable. Okay? But we think we've got some plans for that. We will teach you how to be a better teacher, not just of software carpentry, not just of programming, but in general. We will introduce you to a community that is as welcoming and supportive as the one you're in right now. This will be useful and it will help you and you'll get to meet lots of people. And if you weren't looking carefully at the map, okay, we actually do run workshops in places like Hawaii. Hands up if you've, just not interested in ever visiting Hawaii on somebody else's. Yeah, okay. Now, occasionally we run workshops in Sweden, but everything balances out. So, I know. Why pick on Sweden when Finland is right next door? But okay. What's the one thing the Swedes have that the Finns don't have?
Patience.
Good neighbors. Okay, that joke never gets old. Yes, most of our training has been done online and remotely, and this is why we've had to rethink it. I'm running an increasing number of classes this way for institutions that partner with us. But that's not going to help us grow into the rest of the world. We've only ever run workshops in Brazil. We've never run workshops anywhere else in Latin America. Okay, that's just wrong. We could fix that. We've been to Ghana once and to South Africa a few times, but there's the rest of Africa. Right? We've only ever run one workshop in India and one in China. We've never been to Japan. We're not going to fix that if we only ever run in-person instructor training, right? And we really want to reach the people who need our help most. You know, Stanford doesn't need us, right? They can afford to hire one instructor for each undergrad. Because if you've got a $29 billion endowment, what else are you going to do with it, right? We want to reach everybody. Okay? One here, go.
How experienced do you have to be able to do this?
We do not get any extra value out of expert programmers, right? We find that people who are only a couple of steps ahead of what's normal in their discipline are the best instructors, because you remember what it's like to find this stuff confusing. That makes you much better placed to teach people who still find it confusing. If you can do a pull request on GitHub, okay, then I am looking at, no, I've already picked on Gail. Okay, who has an hour tomorrow to give, I'm sorry, I don't know your name. Olivia. Olivia wants an introduction to Git and GitHub. Will she actually get taught that? There you go. Okay, so he is going to teach you Git and GitHub tomorrow. Okay? Talk after class. Right? That's the one technical skill that we absolutely need to have. If you know how to write functions in Python, that's as far as we typically get. If you know how to tell people, here's what I do with computing, here's my real story, they will believe that a lot more than they'll believe some computer scientist who comes in and talks about recursion on GPUs in the cloud. We can help you. Okay? We can heal you. Do you want to know why computer scientists are bad at this stuff? Let me mini rant. I've got time. In Canada, if you want an undergraduate engineering degree to be accredited, its students must spend a minimum of 6 hours a week in the lab doing experiments. And I don't know the numbers for biology and physics, but I think they are the same. You have to know how to do experiments, collect data, analyze it. That's what science is, right? Most undergraduates in computer science in Canada do exactly one experiment in 4 years. Typically in an operating system or networking class, where what they do is collect some performance results, throw away the outliers, calculate the mean of what's left, and pretend that it's meaningful. They've never done science. So it's not surprising that they don't understand what science actually is or how to do it. They have many other useful skills, and I shouldn't diss computer scientists as often as I do, but they fundamentally don't know what it means to construct a model, do an experiment to validate the model, and see whether the experimental results confirm or refute your model. Right? So it's not surprising they have trouble communicating with real scientists. And I'm actually heartened that we slightly, slowly see this changing. Increasingly, software engineering research is empirical. Let's go and study what real programmers do. Let's gather data from GitHub and SourceForge, and let's go and analyze millions of lines of source code and look for patterns. And in order to do that, you have to know what an experiment is and how to do statistics. And that stuff is very, very slowly seeping into the undergraduate. I think that 10 years from now, it will be much more common to find computer scientists who know how to do experiments in the sense that astronomers do experiments. They go and gather the information that's out there. They have no control over star formation, but they can watch it and analyze it. And they will be much better placed to talk to real scientists about their needs. Okay. I've been talking way too long. Thank you all for putting up with it. My email address is easy to find. I'm gvwilson@softwarecarpentry.org. We need lots of help with our lessons. We need lots of things, and we'll give back as much as you give us. I hope you found some of this useful. I look forward to seeing you in the classroom someday. Thank you.